to remind you that there is coffee, good coffee all day around. So that's nice if you want to stick around here. So you can take coffee at any time, you know, the machines, especially if you want to stick around in the afternoon coffee break and after you're done with the experiments. So I would now changing program. I think we made a mistake when we removed the discussion, the question session this week. We wanted to make not too long in the morning, but I think that wasn't a good idea. So starting today, there is a changing program. After the last talk, so after the third talk in the morning, we'll have 30 minutes general questions, like last week. So you're super welcome to ask questions during the talks, any of them. And after, we have these 30 minutes general questions, starting today. So that means that instead of ending 12:30, we will end at 1 p.m., right? That's not an issue, so we will start at 2:30 instead of starting at 2 in the afternoon. So we shoot everything for 30 minutes, right? And in USP, we'll do the same. So yesterday worked very well. We took this Uber, we went for lunch, and we were ready for the experiments. That's working well, so that's the change, okay? And also, we welcome the speakers if they want to be in the afternoon coffee break for discussions, etc. It's not mandatory, but it's if you can attend of some of them, that would be nice so you can have more informal chats. Yes, and of course, you're welcome to visit the experiments upstairs. We won't take you to USP unless you want. It's possible. There's a reactor there, for example. But yes, so and today will be chaired by Edivaldo, who's a member of the organizing committee. And without further ado, let's go with Dan. Thank you.
Yeah, thank you. Great, my mic's on. So good morning, folks. So today I would like to talk about neutrino interactions and how we can use neutrino scattering to learn something about both fundamental physics and how it can help support other experiments like oscillations, which are studying fundamental physics. So this is a power plant in Rio de Janeiro state, just 100 kilometers or so away from here. And within this power plant complex, there's a nuclear reactor where we do have a scattering experiment that I'll talk about later. And yeah, so we'll again start by talking about different scales that neutrino scattering can happen at. So these energies that appear in your detector vary anywhere between keV and TeV and above. And really this changes the fundamental properties of how the neutrinos scatter with the nuclei. So this really all comes down to the de Broglie wavelength. There's going to be some momentum transfer. You're going to exchange some W or Z boson. If that de Broglie wavelength is very large compared to the size of the nucleus, then you get very small energy deposits in your detector. That's this keV scale. This is what sevens is. This is sevens is basically something that happens when the de Broglie wavelength is so big, the nucleus looks like just a point particle, and all the complicated nuclear physics just gets integrated out of it, and you end up being able to predict the cross-section actually very well. If we go to the other end of the spectrum at the TeV scale, this is the region where we also understand neutrino interactions very well, but for different regions. Here, the de Broglie wavelength is just incredibly tiny. It's small. You're basically picking up individual quarks that you're scattering off of. And there you have, neutrino quark interactions, fundamental particles versus fundamental particles. We can model that very well, and we therefore understand scattering in this regime very well also. These two middle problem children are the things that we really have to worry about in measuring cross sections for supporting other measurements. So at the MeV scale, this is a scale where nuclear physics happens, so you get a lot of neutrino interactions, and you get a lot of neutrino scattering channels. But unfortunately, we don't understand the scattering of how neutrinos bump protons and neutrons up to excited levels in the nucleus so well. And so we're still working on understanding what cross-sections look like in this regime. This is going to be very important for our astrophysics lecture tomorrow. And then if we go up to GeV scales, here you similarly have a lot of messy physics. You're scattering on individual nucleons, spitting them out in different ways, which can produce different particles with different kinematics in your detector, which can bias energy estimates and really mess up oscillation results that you might want to get. So yeah, these at the very low end and very high end, we understand neutrino scattering pretty well, and we'll use them to understand fundamental physics. But in this interior region here, there's a lot of additional things that we need to just learn about the scattering processes themselves. So without further ado, let's just start from the low scales. Let's start with 7s at the KeV scale. And yeah, why this is really interesting. So I really like thinking about the 7s in terms of dark sectors. So if you think about the standard dark sector, you have standard model particles, which are we understand and we know how they interact. But maybe there is some hidden sector here, which can interact very, very weakly through this new force, which we call a portal. And just the general characteristics of a dark sector particle is, well, they have to be electrically neutral so that you don't see them in your detector. They have to have very feeble interactions with the standard model and be very light. And then 3, you do need to have some interaction with the standard model, which is going to happen through some portal. So these are the definitions of really what make a hidden sector. And if you look at these definitions, we do have one particle. It's a neutrino. The neutrino is a hidden sector. This is the portal. It's the weak force that it interacts with through with the rest of the standard model. And if you go back to the postulation of the neutrino back in the 1930s, we really didn't have any understanding of any other aspects of the weak force. We were really just trying to understand beta decay, and the neutrino was the hallmark that there was an extra W and Z set of bosons up at higher scales. So yeah, this is a historically interesting thing to think about, these hidden sectors, and how these might interact with 7s. So the standard 7s picture up here, you have a neutrino comes in, gives a little tiny kick to a nucleus, which you measure in your detector. This also connects up very cleanly with oscillations. So instead of just having the standard Feynman diagram for 7s, which is on the left here, if you have some additional neutrino non-standard interactions, it will interfere with the standard model Z-mediated process. And the extra force, the portal, is just in some effective field theory here, so it's just in the blue dot. And that matters a lot for oscillation. So if you look at just the oscillation Hamiltonian, you saw this in the first week. That depends on both the vacuum portion of the oscillations, but also some matter effects. So if you add additional matter effects, which may vary for different flavors, you can completely change the phenomenological things that you observe in oscillation experiments. That gives you a huge ambiguity, which you're seeing in the bottom plot here. So this is basically looking at these epsilon parameters, are strengths of these extra NSI forces. And then the LMA is this sort of the standard oscillation picture that we have here. And LMA dark over here, this is a second set of oscillation parameters that also fit the data, but requires some sort of NSI contribution. So we really need, and this green here is new data coming from coherent from 7s experiments. So we need data from 7s to basically either choose one of LMA dark or the standard oscillation scenario. So we need fundamental scattering experiments to resolve these oscillation ambiguities. There's also applications to dark matter. So this is very relevant for the accelerated dark matter portion of the lectures here. And similarly, you can have hidden sector particles that are produced in these proton-mercury interactions in, say, a beam dump experiment, which can decay and produce dark matter particles, which can go and scatter in your 7s detector. This will give you an additional component of your data spectrum. You'll see more events because of this. And the problem with galactic dark matter, which Javier went over yesterday, is it's slow. The beta of those particles is sort of a few parts per mil. It has to be less than the escape velocity for the galaxy. So if you look at the recoil energy distribution here on the bottom left, this pink is sort of the expectation of what you would expect for galactic dark matter happening in a typical 7s experiment if the dark matter has a mass of about 25 MeV. So yeah, but if you go to accelerator-produced dark matter, you get this blue distribution. At accelerators, you can produce the dark matter relativistically, so you can give a lot more oomph in the dark matter nucleus interactions. And so Javier said that if you have thresholds low enough, the galactic dark matter experiments will win over the accelerator experiments. You see that, so the galactic dark matter goes up 5 orders of magnitude, and it's suppressed by 10 orders of magnitude on the scale. But the accelerator-produced dark matter gives you energies about 1,000,000 times higher than what you would get in the galaxy. So for low-mass dark matter, these accelerator type experiments are very efficient probes of the parameter space. Yeah, so sevens, the coherent elastic neutrino nucleus scattering, just the name carries a lot of weight. So just really quick, what does coherence mean? So in the standard model, you have a neutrino which scatters off of a bunch of stuff in the nucleus. So you will basically add up the matrix element for all those individual things, all the individual neutrons and protons. Since they're all in the same place relative to the size of the de Broglie wavelength, you will add them up coherently and then square the matrix element. So that means that the cross-section will go like the square of the total weak charge in the nucleus, which includes some contribution from protons and neutrons. It turns out that this pre-factor for the protons is this factor right here is almost 0. And so that means that basically the neutrons win, and the cross-section basically scales like the number of neutrons squared. So that's what coherence means. And then elastic scattering. So if you elastic scattering basically just means the particles aren't changing in the initial and final state. You're just knocking a neutrino off of the nucleus and send it recoiling with a little bit of momentum. And so how much kinetic energy does that nucleus actually get? It's non-relativistic, so you can just use p squared over 2m. And so you just have to think about the momentum transfer from the neutrino to the nucleus. So the momentum transfer Q is, since the energy isn't changing that much, since you don't pick up so much recoil energy on the nucleus, this is basically just the change in the 3 momentum. The maximum change in the 3 momentum is 2 times the neutrino energy. That's the case where the neutrino comes in and out in the exact opposite direction. So that momentum transfer is less than 2 times the neutrino energy. Plug that into p squared over 2m, and you get something like 2 times the neutrino energy squared over the mass of the nucleus is the maximum recoil energy. So if you have a 25 MeV neutrino scattering off of a cesium atom, that gives you 10 keV. Very small, but we talked about yesterday scintillators can get thresholds that approach that level. So we should be able to measure this. So yeah, these are just the energy scales, 25 tens of MeV of neutrino energy, and recoil energy tens of keV. Yeah, so how much are we actually going to see in our detector? How many photons do you think we can get? So let's start. Yeah, this is just our typical sevens detector, just a bunch of scintillator, maybe monitored with a PMT up on here. This is exactly like the setup for the coherent cesium iodide detector. And let's just put initial energy of 10 keV on some nucleus inside this detector. How many photons are we going to get out? So the first thing that we have to deal with is quenching. So if you just shoot a nucleus inside your crystal, it's mostly just going to bounce around and give a little bit of heat to the lattice and lose energy that way instead of making photons. Usually that quenching can be as much as 90% is lost to thermal energy. So really you only get about 1 keV of energy that goes into light. So what does that mean? So light yield, usually the typical scales for exciting an electron in an atomic nucleus in an atom is something like 10 eV. So basically take this 1 keV divided by 10 eV and you get 100 photons. So that's how many photons are actually produced in your detector. But you don't collect all those efficiently, so they're going to sort of bounce around on the walls until they hit the PMT. Maybe some of them will die in the PMT. Maybe the quantum efficiency for your light detectors isn't so high. So maybe you collect something like 50 photons in the end, which make it to the PMT. Sorry, now I'm also including the quantum efficiency at the final step, which is usually about 20% or so for PMTs, maybe a little bit higher if you're using SIPMs. So in the end, you only get about 10 photons for this initial 10 keV, which is the maximum recoil energy for 25 MeV neutrinos scattering in this detector. So you're really just up against the battling thresholds in these detectors to measure sevens. So yeah, that's the signal that we have. Now let's find a source where we can actually do this. I'm a member of the coherent experiment, so I study sevens at accelerators at the spallation neutron source in Oak Ridge National Lab in Tennessee, USA. So this is the accelerator that we have. It's actually designed to make a large flux of neutrons. It coincidentally also makes a large flux of neutrinos. So the flux starts over here. You basically have a proton source, which is accelerated in some RF cavities through a LINEC. Some dipole magnets kick it over here and send it into an accumulator ring. The initial proton source sends out on order of gigahertz little proton bunches which end up in the accumulator ring. They integrate up, and then 60 times a second, they dump the accumulator ring here onto a mercury target at number 5 here. Within the mercury target, you produce a large flux of neutrinos, which can be monitored in neutrino experiment detector halls that we have here at number 3. And yeah, just a few numbers here. So right now, the accelerator is being upgraded from about 1.4 megawatts to about 2.1, which will be completed in a few years. The proton energy is right around 1 GeV, runs at 60 hertz, and delivers pulses with about 350 nanoseconds width. So yeah, this is the basic target that we use. So we use liquid mercury. So liquid mercury is a toxic element, so why would we do that? So this is a neutron producing accelerator. You want to produce a lot of neutrons. You want to have a heavy element that can boil off a lot of neutrons really easily. But the limiting factor for these accelerators is often cooling of the target. So the wonderful thing about mercury is it's a liquid at room temperature, so you can just cycle the material in this target through a heat exchanger and cool it quite rapidly so that you can maintain this couple megawatt beam power. And if you look at if you do some giant simulation of 1 GeV protons hitting on this target, you'll see that you'll produce about 0.1 pi pluses, which we'll see gives you about 0.3 neutrinos for every single proton hitting this target. So how does that happen? So yeah, we have protons hitting mercury here. So lots of interactions. You can make charged pions in those strong interactions. The pi minuses will end up getting captured around a nucleus, basically swap out for an electron in an atomic orbital and capture on the nucleus. So these don't give you any neutrinos. But the pi plus can't do that, so they'll just basically come to rest somewhere in the middle of your target and decay at rest, giving you a muon and a muon neutrino. That muon will similarly come to rest and decay to a positron and an electron neutrino and a muon antineutrino. So there are two processes giving you 3 different flavors of neutrinos, and they happen at different time scales. So this pion decay has a lifetime of 26 nanoseconds. The muon decay has a lifetime of 2.2 microseconds. So if you just look at the flux, we have this really nice distribution of prompt neutrinos coming from muon neutrinos, and these delayed neutrinos coming from electron neutrinos and muon antineutrinos. I won't get into it too much today, but this is an incredibly important plot. A lot of the fundamental physics searches that we do in Coherent rely somehow on this, either weighting different flavors of different sevens interactions differently through different NSI scenarios, or looking through dark matter which might scatter promptly in this region. So really weighting the prompt to delayed region gives us a lot of power for searching for new physics. And also the energy spectrum you see down here, this is incredibly well known since over 99% of our neutrinos come from decay at rest. That gives you these easily calculated distributions here. And then you have about 1% tail coming from various decays and flights and other types of neutrino production. So this is it. This is the flux that we have at the SNS and gives us a very well understood flux. So we can go ahead and measure that. Yeah, sorry. Yep.
Can you talk a little bit about like the really sharp peak that you have in the
This one?
muon neutrino distribution? Yes.
Yeah, so that comes from pi plus decay. It's a 2-body decay, so it's monoenergetic. Right. Yep. And then these other are 3-body decay, so there's some distribution. Yep.
Thank you.
Yep. Thank you. And yeah, I stumbled a little bit on getting to this slide, so thanks for asking the question. So really, we want to measure sevens at this facility, so how massive of a detector do we need? So let's just say that we want to build a detector that will record about 1 sevens interaction each day, 20 meters from the SNS target. So let's just think about how many protons we're actually making in our beam. So, well, we have 1.4 megawatts of beam that's produced by 1 GeV protons. So just take the ratio of that, that gives you the number of protons, multiply by the number of seconds in the day, that gives you something like 8 times 10 to the 20 protons produced at this accelerator. This accelerator also gives you an insane number of protons. So you actually measure the protons in like grams per year, which is pretty insane to think about for me. And then we also just take the number of pions, this is the number of protons times 0.1. So this number, the number of neutrinos is 3 times that, since you get nu mu, nu e, and nu mu bar. So we're up to 2 times 10 to the 20 neutrinos per day. And then divide this, spread this out over a sphere of radius 2,000 centimeters, and, well, critical typo, that should be 5e to the plus 12 per centimeter squared neutrinos produced per day, the fluents. And so the number of sevens interactions will be the number of targets times the cross-section times this flux. So we can work out the number of targets that we need in our detector just by taking the ratio of these. So let's say we want 1 sevens divided by a cross-section, which is 1 e minus 38 over here in the middle of our beam energy window, times this flux that we have. If you plug in the numbers, you get something like a few times 10 to the 25 cesium or iodine atoms, which is about a few kilograms. So just back of the envelope, you can see that you can really scale down your detectors and have a handheld detector and measure these sevens interactions quite well. And yeah, the answer that we got was 14.6, so pretty close to the back of the envelope calculation. So yeah, this is the actual coherent experiment. So we're at a neutron accelerator, so neutrons are kind of crappy backgrounds for neutrino experiments. They're neutral, so they can enter into the middle of your detector, but they're strong, so they interact pretty strongly once they're in there. And so the first thing to do is really find a place in this accelerator that is neutron quiet. So the first couple of years of coherence experiment lifetime was really just going down with some neutron cameras all across the accelerator and find some place which is reasonably neutron quiet. We found this, which we call Neutrino Alley, which is just a basement hallway, very unimpressive until we think about the neutrino and neutron fluxes. That was initially built for utilities, like taking off hot gas from the accelerator and cooling water. And we see that we actually have a neutron flux low enough here that we can do these sensitive neutrino measurements. And so this is a diagram of Neutrino Alley. We will implement many detectors here. We have, I think, 10 running right now at baselines between about 20 and 28 meters from this SNS target. And the different neutrino detectors that we have here run the gamut. These two are measuring sevens on argon and sodium. This is looking at inelastics on thorium, actually looking at neutrino-induced fission, which has never been observed before. Gemini here is looking at sevens on germanium. Deuterium, heavy water is looking at neutrino interactions on deuterium, and these NIN cubes are looking actually neutrinos spitting neutrons out of nuclei in lead. And right now we have measured sevens on cesium, iodide, argon, and germanium, and we have an ongoing campaign for sodium. We also have a lot of detectors studying inelastics right now. Yeah, so let's just think about the cesium iodide result, some of the things that you have to worry about for the analysis to actually make happen. The first is this problem called quenching. So a lot of the initial energy of your nucleus goes into just exciting the nuclear lattice. That's sort of just energy that you lose. It doesn't go into photons, so you need to calibrate that very well. So what you do is you have a little sample of your detector material here connected to a photon detector. And then you just shoot a neutron beam in here, and then a neutron comes out recoiling and is measured in one of these liquid scintillator detectors. And given this angle, you can understand exactly how much energy you gave to a single nucleus in this sample. And then you can just look at how much energy, how many photons you saw coming off of that recoiling nucleus, and basically just calibrate this amount of visible energy that you see versus amount of energy that you put in, which is exactly the curve that you're looking at here. And all of these, well, the top 5 measurements are all from coherent different groups. And then we have 2 additional groups that have looked at quenching factors in cesium iodide. They give you this distribution for the so-called scintillation energy curve. And doing some fit gives you some understanding of what the quenching factor is. It turns out to be about 8 to 10% in cesium iodide for the region of interest. Yeah, so the next step is just doing your reconstruction, the waveform analysis. So these detectors are simple scintillators, so you just have a single PMT on top monitoring all of your light. And so all that you have is this little voltage waveform that, you see a few little spurious counts over here. These are background scintillation within the crystal that you just randomly acquire. And then here, this dashed gray line, this is where your protons on target are actually happening. So this is where you expect your neutrino pulse to start happening. And then you see right after those POT, you get a big forest of photon pulses. So this is, likely a neutrino event. It could be a background that was just coincidentally very close to the arrival of the neutrinos. And the really fantastic thing about being at an accelerator is not only when your neutrinos are coming. So you can look at all of your neutrino signal in this region, this so-called coincidence ROI, the CROI, but you can estimate all of your steady state backgrounds by looking at this ACO-ROI, the anti-coincidence. So this is in before the neutrinos arrive, so you know that there isn't any signal. Anything that you see there has to be background. And so this is just an excellent way of, you don't have to simulate your backgrounds, you just measure them in situ. So there are no systematic errors associated with that. And yeah, so the last thing that you really have to worry about is your efficiency for tagging nuclear recoils. So I mentioned earlier, we're really just right on the threshold for these experiments. Yeah, a question? Yep.
Thank you. Just to clarify, ROI is region of interest?
Yeah, just where you expect events to happen. So it's just a specific time window where we expect either the neutrino signal events or your background estimate.
Okay, thank you.
Yep, thanks. Yeah, so these detectors are right on threshold, so you really have to worry about your efficiency. So you want some way to calibrate that with data also. So we have this barium-133, which is a gamma decayer. So it's going to shoot gammas in your detector, and similarly, you can have a backing detector here at different locations. So you can look at coincidence for a barium decay and gamma also in your detector here. And similarly see the deflection angle of your photon, and that's going to give you a Compton electron with a specific amount of energy. And so you can basically look for ability to select that little Compton electron versus how much energy you know that you had go into that Compton. And that gives you this calibrated efficiency curve versus, well, the black data points are exactly from this barium data set, and then the blue is some fit giving you some predicted value for your efficiency along with some systematic error for that. And okay, yeah, that's those are the main hiccups for actually making these sevens result, at least for cesium iodide. Once we solve that, we can now bask in glory of actually discovering sevens here. So this is the energy spectrum. The different colors here are different flavors of neutrinos. And then on the bottom here, you have the time spectrum. Again, I'll just point out that you see this prompt nu mu flux very early in time. And then you see these exponentially decaying with a lifetime of the muon lifetime components from nu-e and nu mu bar, also producing sevens. And this is from cesium iodide from our first detector that saw sevens, but we saw sevens in argon at about 3.4 sigma. And that's this is just a simple argon calorimeter. This was in 2021. And then just at the end of 2023, we also saw this in germanium, which is a different type of detector. It's a PPC detector, so it's basically a big diode with 2 kilograms of germanium in it. And the electrons that are ionized in a sevens interaction will drift given the bias voltage that we apply. And similarly, in all these different detectors, we can measure both, say, the prompt here and delayed neutrinos and look at the calorimetric energy to try to understand how we can look for new physics, new fundamental physics in these samples. Unfortunately, I don't have time to get into that, but it's fun. Ask me. This is sort of a selection of the physics that you can do. So, yeah, sorry, question? Yeah, so differentiating the flavor of the neutrinos. So a lot of that comes down to this timing plot. So there you can separate out the mu and the mu bar plus electron. So a lot of BSM models will say the mu and mu bar sevens interaction, sevens cross sections change in the same way. So you can basically use this prompt brown peak to normalize how this orange nu bar peak should also look like, and then really measure the excess gold NUI on top of that. And so really using the timing, you can separate out those two flavors. If you have really fantastic large detectors with good energy resolution, you can also do that calorimetrically. If you stare at this plot, you'll also see different differences in all the different colors. But we need, basically more exposure to do that analysis reliably.
Okay, thank you.
Yep. Yeah, so this is a selection of the physics that we have here. There are hundreds of papers that have come out of using SEVN's data to look for new phenomenological BSM physics. So yeah, more than I had to get into, but feel free to ask me about any of these things that you see on the slide. And yeah, just a little bit quick reminder that coherent is not the only experiment looking for sevens. There's at least a dozen looking for sevens at neutrinos. So probably the closest to detection I'll give is CONUS right here. So this is similar to our germanium detector within coherent. These are PPC ionization germanium detectors. So basically these diodes, which are at a nuclear power plant. So this is the reactor facility. The reactor's, I think it's this. And then the detector assembly is right here. So there's a huge composite shielding right here with a few ports for calibration. And then the actual detectors are housed in here. This is cold head, keeping the germanium detectors at liquid nitrogen temperature, 77 Kelvin, through the cryogenics here. And within here, you will see about 1 kilogram of germanium crystal, and 4 of those within their detector. So if you look at their results right now, so this is state of the art, what they were able to do. And unfortunately, they weren't able to see sevens, but they were pretty darn close. So this is the sevens expectation compared to their data that they see here. You see it's kind of on the right scale, but not quite there. They were able to put a limit of 2 times the standard model cross-section for the cross-section at reactors. And yeah, but right now they are basically upgrading to CONUS Plus, which they're upgrading their data acquisition electronics, which will allow them a threshold improvement from 210 to 150 keV. If you look at the standard model prediction right here, it's basically exponentially rising. So if you get to this 100 keV, 150 EV, sorry, not keV, you will be able to see sevens at the reactor pretty darn soon. And then just one more quick word about CADI. So this is, you'll have a lecture on basically this technology on Friday, but this is using Skipper CCDs, just tiny little pixelated detectors right here that give you nice, basically tracking information of sevens interactions and backgrounds in real time. And really the phenomenal thing about CONI is how well you can estimate your ionization energy. So each one of these peaks is it's an integer number of electrons that are ionized within your crystal. And this will go out to a few thousands. And then right now, this is a recent limit from this year coming from CONI. It's unfortunately not that competitive. It's about 32 times the standard model cross-section. But they're upgrading they just installed a large detector with multiple Skipper CCD units, which increase the active mass to about 32 times what was produced in this plot here. And this is the experiment at the Angro reactor, which I showed on the first slide in Rio de Janeiro. Yeah, so with that, I used half my time on sevens. I was hoping it would be a little bit less, but okay. So now we're on to the MEV scale. So this is the inelastic sort of nuclear process regime. And the 3 main players that will come up a lot tomorrow are inelastic scattering on nuclei, inverse beta decay, and neutrino electron scattering. So let's talk about each of those 3 processes. So inelastic scattering, it's sort of a messy scenario. You're starting to deal with nuclear physics. And if you think about atoms as sort of a collection of electrons in different electric orbitals, you'll need discrete energies to excite an electron to an upper orbital. A nucleus is basically the same thing. It's a collection of neutrons and protons, which are also fermions, and will have a structure like this, analogous to an electron state structure. And these are states for various protons and neutrons in a specific nucleus. And what neutrinos will do in this energy regime is basically bounce protons and neutrons between sort of ground states and up into excited states. And so you need to understand exactly the matrix elements for transitioning between those states, which is not a very straightforward calculation to do. But yeah, so one example that we'll use tomorrow is neutrino scattering on argon-40. Argon-40 is, the basic detection medium for argon detectors, TPCs. So this will be important for Dune and their astrophysics agenda. So when a neutrino hits an argon-40, it makes a potassium-40. But it turns out that this potassium-40 is always excited. So it's always going to give you a few little de-excitation gammas along with an electron track. So this is looking at solar or supernova neutrino interaction in the Dune TPC, which again you see here an electron track along with a few blips from Comptons from the de-excitation gammas here. And so right now we're starting within coherent. We have a flux of low energy neutrinos below about 50 MeV. These are sort of perfect for testing this inelastic scattering regime. And so we have our first measurement already out, which is looking at the analogous interaction on iodine-127. So neutrino is absorbed by the iodine-127. It releases a few de-excitation gammas, and an electron comes out. This is an array of 24 7.7 kilogram sodium iodide scintillators, each with a PMT on top here. And if you look at, this is the result that we get. So the analysis here is basically look at the timing. Only the electron neutrinos are going to produce these charge current interactions, so they'll be delayed neutrinos. So you will have some characteristic decay with a decay time of the muon lifetime, which we can observe, and separate out from prompt to neutron backgrounds and steady state backgrounds here. And the inset here gives this nice decay function along with the data excess that we see. So we are clearly seeing an excess from these inelastic interactions. And then one thing that we can do is we can start to understand what kind of particles are coming out of this interaction. One thing that you can do is instead of just spitting out de-excitation gammas and electron is you can also shoot out a neutron. That's a problem because that will bias basically your energy. Neutrons are very hard to detect, so it might detect if you are studying solar neutrinos in Dune. So you really want to have some way to picking apart events that spit out a neutron or don't. That's what you're looking at in this plot down here. So this is an actual cross-section that we reconstructed. The y-axis is this sigma 0n, 0 neutrons produced, and greater than or equal to 1, n means that there is at least 1 neutron produced. And you can see here, this is our data. So this is sort of where we think nature lies. This blue band is a past experiment that was explicitly only looking at the 0 neutron emission case. And then this red is the current best estimate from theory. This is an event generator that was calculating the prediction. You can see that sort of the best fit is kind of far from this best fit, this theoretical prediction. That's really just underscores the importance of doing these measurements. Right now we don't understand how the neutrinos interact on matter so well, so we need to make these measurements so that we can, in the future, when Dune is running, study solar and supernova neutrinos with in an unbiased way. Yeah, so the next here is inverse beta decay. So this is an anti-neutrino scattering process. So there's one very special nucleus, the hydrogen nucleus, which is just a nucleon. It's not going to have this forest of excited states above the ground state. If you hit a proton, it's just going to go to some continuum state. It's just going to get some momentum. And so that's exactly what you have here. You have the anti-neutrino comes in, knocks on the proton, and makes a neutron and a positron. So if you look at this in, say, a water Cherenkov detector, this positron is going to make a ring of Cherenkov light. And then the neutron is going to scatter around and eventually thermalize. And if you have gadolinium in your detector, the neutron will capture on that gadolinium and produce about 8 MeV of gammas, which is also visible in your detector. And yeah, you get coincidence of these two signals, which is fantastic for background rejection. It also has a pretty large cross section, about 10 to the minus 42 centimeters squared at 5 MeV. And yeah, if you think about really the pros and cons of this interaction channel, Pros, it has really fantastic background rejection. It's also a very well understood cross-section, since you're just scattering on a nucleon instead of a nucleus. It is a charge current interaction, so the visible energy that you get is exactly equal to the neutrino energy minus 1.8 MeV. Where does 1.8 MeV come from? That basically comes from the mass of the neutron plus the mass of the proton plus the mass of the positron minus the mass of the proton. It's the amount of energy that you have to, it's the threshold energy, the amount of energy that you have to put in to make these final states. And that visible energy is very correlated with this prompt energy. Yeah, the cons here is it's really only sensitive to antineutrinos. The analogous neutrino process would be a neutrino comes in, scatters off a neutron, but free neutrons are difficult to have in a detector. And so, yeah, you really only see the half of the aspect of whatever process made this neutron flux. Say a supernova comes in, you measure the antineutrino flux with inverse beta decay. You don't learn anything about the neutrino flux coming from that supernova, which is unfortunate. So we'll talk about that tomorrow. And then there's also neutrino electron scattering. So this, all flavors participate in this. And you have either a neutral current or a charge current that is producing this interaction. But the charge current is only mediates the electron neutrino channel. So for electron neutrinos, you get basically interference between these two terms, which gives you a relatively large cross-section compared to the other flavors. Whereas for the nu mu and nu tau, you just have the weak neutral current here. And so if you just look at the cross-sections, these are the cross-sections for the all flavors. This is about an order of magnitude higher for electron neutrinos than for nu mu or nu tau, and similarly different for nu e bar. This is very important for oscillations. So you heard about it in the first week. Does anyone remember why? Sorry? Exactly. This is exactly what gives you the matter effect. This is what lifts a lot of the degeneracies in neutrino oscillations. So this is a fundamentally very important thing that we'll talk about on Thursday. But yeah, so this will also be important for astrophysics, so solar supernova neutrinos. The pros here is it gives you directional information. So this is, the electron is pretty light, so it ends up being, the direction of the electron doesn't change much relative to the neutrino. The cross-section is also incredibly well understood. This is just scattering between two fundamental fermions. And really all detectors are sensitive to this since you're scattering off of electrons. All matter has electrons in it. The cons, the cross-section is just tiny. This is 10 to the minus 45 centimeters squared versus 10 to the minus 42 for inverse beta decay. And the energy estimate is pretty poor. So that is it for what we have at MEV scattering regime. So now let's go on to this GeV scale where basically everything is really complicated. If you go back to the de Broglie wavelength, this is just at the scale where the de Broglie wavelength is the size of an individual nucleon. So really all the aspects of QCD is combining in very complicated ways to give you, to just mess up your understanding, make it difficult to understand how neutrinos are really interacting in this dense nuclear medium. There are three processes that will contribute here. There's quasi-elastic scattering, resonant pion production, and deep inelastic scattering. So we'll talk about those in just a minute. So this is a famous plot. Probably most of you have seen this. And so if you look at where oscillation experiments typically lie, what energy regime they live in, it's usually most convenient to make those at accelerators, which is very good. Accelerators are very good at making GeV neutrinos. So oscillation experiments are going to sort of live in this regime here, which is also the regime where you have maximum pileup of all these different types of phenomenologically different neutrino scattering processes in the nucleus. And so we really have to, do detailed measurements of neutrino scattering on nuclei to separate out these quasi-elastic resonant and DIS contributions so that we can understand how in each one of those individual scenarios energies get smeared, which will be important for extracting oscillation parameters, which of course depend on neutrino energy. So one detector that we have to do this is the Minerva experiment. So this is a detector built specifically to measure these GeV scale neutrino interactions and do it very well. And so what it is basically a huge plastic scintillator calorimeter. You have this interior region of scintillator trackers, which is built off of these triangular prisms of plastic scintillators. So these are long bars, a few meters tall, with a few centimeter cross sections. And this green wire in here is a wavelength shifting wire. So light will be produced in these scintillators right out in the wire and connected to I think an APD for their light readout. And all in all, they have about 8 tons of material in this active region. If you go back beyond this, there's an electrocalorimeter and a hadronic calorimeter, very much reminiscent of experiments at the LHC like Atlas and CMS, which have sort of tracker, ecal, hcal, onion type structures in much the same fashion. This will help capture all the all muons and long-lived long-range particles that are produced in your neutrino interactions. Up in front of the detector, you have, well, first a steel shield and then just a little plane of scintillator veto. This is so you don't have any interactions from upstream in the rock making it into your detector. And then you also have a little liquid helium target right here. Helium is just a simple nucleus, so if you look at neutrinos on that nucleus, it's sort of the simplest medium that you can consider and study that still has all these complicated effects. So it's also nice to have scattering on helium. And then up here, you also have a region where you can swap in a lot of different targets. So carbon, lead, iron, and water are all swapped down in there so that you can understand not just nuclear scattering off of nucleus in for one type of nucleus, but over a variety. And yeah, so one thing that you really have to understand is what the neutrino flux looks like. So this is data plot with more information than this. It's basically saying that all the neutrinos oscillation experiments are living somewhere in the 0 to 10 GeV regime. But Minerva has 2 different flux settings, this so-called low energy and medium energy, which give you the purple and orange distribution here. And you see that the purple, the low energy running for Minerva is basically completely coincident with, say, upgraded with the Dune flux. And then we also have short baseline experiments, mini boon experiments, micro boon experiments, which lie down here on the lower end. So this is an experiment that was really just designed to measure this complicated region as well as possible. So let's look at a few neutrino events. So this is first starting with the quasi-elastic interaction. So an elastic interaction is an interaction where you don't change the particle types. Quasi-elastic interaction is basically the next best thing. You just have an isospin flip in one of the nucleons in your nucleus. So the muon neutrino interacts with a neutron. That neutron becomes a proton, just isospin flips. And then you also make a muon in the final state in this charge current interaction. And that's exactly what you see here. Muon neutrino comes in, makes this proton, which is highly ionizing, so you get a lot of charge deposit here. And then you get a long minimum ionizing muon. You can similarly do this for antineutrinos, where instead of scattering on a neutron and making a proton, you would scatter on a proton and make a neutron. So this would be invisible, and maybe you'd have a little bit of delayed deposit from a neutron to proton charge exchange in your detector. Yeah, so the really nice thing about quasi-elastic events, it's just a 2-body scattering. You have, muon neutrino, neutron comes in, proton and muon comes out. So there's really only 2 things that you need to specify that interaction. In the center of mass frame, you need to specify the total center of mass energy and the scattering angle for the outgoing muon. So if you just measure 2 things and you know the direction that the neutrino came from, you can completely understand the kinematics of this interaction. And so usually we do that by measuring the muon, both the direction and the energy. That's 2 things that you measure, so you completely solve the system. And you can just write down the neutrino energy as a function of those 2 things. This extra EB is a binding energy, which relates to basically the ground state to continuum scattering state for the nucleus. Yeah, so that's also nice in scattering detectors like this, tracking calorimeters. You can explicitly see the proton, so you can sort of check how well this this 2-body phenomenology is working. Yeah, question? Here, I'm not quite sure. This is a specific of the detector. There might be some dead channels there. This might be a region where they have like a tank for filling with water for looking at a different target. But yes, that's a good question that I don't know the answer to. Yeah, thanks. Yeah, so in detectors like this where you can actually see the proton, you can test this quasi-elastic formula like they say on the bottom, which we'll talk about it in a little bit. But yeah, so now going on to resonant production. So here, instead of just doing a quasi-elastic scattering interaction, doing an isospin flip, here you're actually exciting a little resonance over the proton. So basically making, okay, yeah, this is pi0 event. So we're scattering over on a neutron and exciting that neutron to 1232 MeV resonance of the proton, a so-called delta, which will decay to a proton and a pi0. And so this, now in your detector, you see 3 particles. You see the outgoing muon like before, and then you have a recoiling proton, and you have a pi0 here, which decays in 10 to the minus 16 nanoseconds to 10 to the minus 16 seconds to 2 photons. And so you see 2 electromagnetic showers right here and right here. And so this, there's a lot of kinematics that you can do. You can, say, measure the proton energy. You can measure the 2 gamma energies, look at the invariant mass, check that that is close to the pi0, and then check the invariant mass of this pi0 proton system. That initially came from a delta, so that should give you pretty close to 1232. And so that gives you like a really distinctive topology in your detector that you can use to check that we are actually seeing the energies coming out as we expect. And that gives us a lot of confidence that our models are doing what we expect for neutrino nucleus scattering. Yeah. Think of it.
The delta is the proton with a higher spin.
Something like that. It is some collection of U and D quarks, which decays strongly to pions and protons. I don't know if just think of it as a higher spin state is the best way to think about it, but it's some collection of those quarks with something. Yeah.
Okay.
Yeah. And then the last thing, the way that neutrinos can scatter at these regimes is deep and elastic scattering. So here, right here is the neutrino vertex. You again have a muon come out in this interaction, but you just have a bunch of hadronic tracks, which are all piling up here in a complicated way. And so what you're starting to look at here, DIS scattering, is really scattering off individual quarks, so basically making a jet analogous to what you'd see at the LHC, where an individual quark comes out of the nucleus and just sprays into a bunch of hadrons, which is what you're seeing here. And yeah, so you really need to understand understand that the quasi-elastic, the deep and elastic scattering cross-section is turning on exactly when you would expect, and that you are getting these complicated hadronic showers at the right energies. So yeah, the really recipe for making sure that we understand the nuclear scattering is really to have an event generator, which takes some information about theoretical neutrino nucleus cross sections, convolved with different event kinematics. And so what you're seeing here is a measurement from Minerva, which is breaking out the the muon momentum into both parallel and transverse momenta, and comparing the data across all these different quasi-elastic resonance, different types of DIS, and other components. So see that all these types of different phenomenological scattering channels are adding up in the right way to give you the right total predicted counts. And you can see with the muons, we are actually doing somewhat well. The hadrons are a little bit a different story. And yeah, so the next thing that you have to do is, well, okay, so the fundamental neutrino nucleus scattering is approximately right, but say you make a proton in a nucleus, it's inside a strong, inside a hadronic medium. There can be strong forces that knock that proton around. So maybe the momenta of your nucleons and pions gets smeared out a little bit. And so you can use, basically, test your quasi-elastic formula against predictions here to make sure that everything is working out properly. So yeah, exactly. You take a quasi-event sample like this with a muon and proton, and the momentum, the transverse momentum should be 0. You should be able to work out the parallel momentum. So basically, if you work out the measured transverse momentum, compare that to your theoretical expectation of 0, you can understand how much the nucleus is, battering around the nucleons within the nucleus, how much they're changing the momenta. And that will tell you something, like the plot down here. This is telling you exactly something about the momentum of the nucleons within the nucleus that you're scattering off of. These are fermions, so they're not going to all be in the ground state. They're going to have some momentum associated with it, and that is exactly given by this distribution here. The data here fits, not so great with any model here, but people are starting to understand this a little bit better and use these sorts of measurements to refine those models. Yeah, the last thing that I'll say is, when you produce a hadron within the nucleus, it can get, battered up a little bit, but it can also have change, flavors. It can, protons can change to pions and vice versa. And so there's in this complicated medium, there's a thing called final state interactions where you can get completely new particles coming out, and you can smear out those energies. This is referring to basically resonant production, which I was talking about before. So you have a 1232 MeV resonance, which produces this peak right here. But you see that is getting smeared out a little bit and phenomenally changed with these upper resonances up here, where different protons and pions are getting absorbed or battered around in the nucleus. And so the data right here is actually meshing pretty well this Gini event generator that we see right there. Yeah, so that is it for the complicated scattering regimes. If we go to the TeV region, this is where the nucleus really just gets obliterated. You are scattering off of an individual quark. That quark comes out with a complicated hadronic shower. So this is once we get up to the multi-GeV region. So this is, you see in this plot, we start seeing error bars that are quite a bit smaller than we had, down in here. So that's just a reflection that we understand the scattering pretty well. It's easier to model. And this is really just a quick landscape of what the experiments look like. So down here, this is really in the regime where oscillations happen. This is at the few GeV. And then going up to sort of hundreds of GeV, these are energies that you can produce easily at an accelerator. There's sort of a gap right here right now, and then you get a few points up here. These actually come from IceCube, looking at atmospheric neutrinos. That flux is relatively well modeled, so you can just use the interaction rate to measure the flux instead of the cross-section. And up here, we just do not have the detector mass to measure any neutrinos at. So there, it would be nice to fill in this region between about 1 TeV and about 10 TeV. The answer to how you do that is with phasor nu. So you can make a few TeV neutrinos at accelerators at the LHC. So this experiment, phasor nu, is exactly going to the LHC, going to the Atlas beam crossover, and putting a detector in the line of sight at the Atlas interaction point. And this phasor detector basically has here like a large tracking detector, a few time-of-flight chambers here to measure both the momenta and speed of particles, which will allow you to determine what kind of particle it was, separate between pions and muons and protons. And that will, we're getting just the very first data from here. So this is something like 150 neutrinos produced in LHC collisions. And this is just looking at the momenta of muons that are coming out of charge current interactions. And you can see it's looking fairly well, consistent with expectations. And this is sort of how well we expect the phasor nu experiment can plug in this region where we don't have direct scattering measurements yet. But this is just a sensitivity, so wait a few years for phasor nu to collect statistics, and we'll be able to say something in that regime. And yeah, so with that wraps up today. We have to study neutrino interactions from everywhere from the KeV to TeV scale. The KeV scale is really interesting for fundamental physics. This is the Sevens regime where you can look for NSI neutrino interactions, non-standard electromagnetic properties of the neutrinos, searches for dark matter. A lot of really interesting stuff that I love to talk about there. So find me and ask me questions if you're interested. And then also in this MeV to GeV scale region, this is where a lot of the other really interesting neutrino experiments happen. So we'll talk about the astrophysics neutrinos tomorrow. That is really going to rely on the MeV stuff I talked about today. And then oscillations we'll talk about Thursday and a little bit on Friday, which will be really important, which will rely really on this GeV scattering. So yeah, thank you. And any questions?
Thanks, Daniel. Questions for Daniel? No. Oh, there's one there.
Hi, I'm sorry. I had a question about the graph in slide 38.
Okay.
That one, because yesterday you showed us a graph like this, and you said in that one we had an electron shower, and then I understood that the energy went to the photon, and that's why you have an empty space because the photon doesn't have charge. But here we have those gammas that like have a charge deposit, so I didn't understand.
Okay. Yeah, the gamma label here basically just means that this is downstream electron and positron charge from that initial gamma.
Okay.
So yeah, it's just a type of nomenclature thing. So these are electron and positron deposits from the photon that is tracked here.
Okay. Okay, thank you.
Yep. Yep, thanks.
More questions? I don't see any, so let's thank Daniel again. Okay. Test again. Hello? No, no, not working. No.
No? Yeah.
So we move to Javier Tiffenberg on the second lecture on dark matter detection. No? Word's yours.
Okay, thank you. Okay, hello. So we're going to continue with the direct detection theme. Today we are going to start focusing on some of the specific techniques other than scintillating crystals that we discussed at the end of last talk. Please, at any point, if you have any questions or things that you would like to say, just do it. Don't wait until the end. You can, yeah, we can discuss anything during the talk. Okay, so at the end of last talk, we discussed that we have a signal from DAMA, but that is a very contested signal, and that there is a huge effort to cross-check it. And so far, all the cross-checks have been negative. Also, that this possible signal, we don't know what it is. And when I say that we don't know what it is, we don't know if it is coming from electron recoils, which is mostly what happens when you have a gamma, a photon, a high energy photon, or a beta that is just an electron moving around, okay? That knocks one of the electrons in whatever target material we are considering. In the case of gamma, we know that there are 3 different elements in the crystal itself: sodium, iodine, and a little bit of thallium. So the other possibility is that we are having nuclear recoils. This is what you would expect because of the cross-section that would happen between neutrons and WIMPs. For neutrons, the reason this dominates over this is that, well, here you have the possibility of the neutron to interact with the nucleus directly in a coherent way, or even in an incoherent way if the neutron has enough energy. And you've been discussing these different things over the different courses, why the low energy enhances the cross-section, so this is much more likely to happen. And also the neutron is neutral, so it cannot directly interact with electrons there, okay? So now, as I said before, we are going to focus on noble liquids. Noble liquids come in many, many different flavors, and we are going to discuss from a fundamental point of view why there are so many efforts using noble liquids to look for dark matter. There are 2 different types of approaches. The original one that was devised for looking for WIMPs, in which you are essentially looking at what I mentioned before, the scattering between the WIMP and the nucleus that then exchange some kinetic energy, and you are trying to see that. And now there is a new generation of experiments that are trying to extend the reach beyond the WIMP to lower masses. And in particular, even to dark matter candidates that interact with electrons instead of the nucleus. Okay, so we're going to focus here, and remember from last talk that we had some checklist that we produce for looking into which targets are good targets for looking for dark matter, and this is kind of our wish list of what we would like to have. Ideally, we would like to have nuclear recoil, electron recoil discrimination if we are looking for WIMPs or WIMP-like particles that interact with the nucleus because of all the things that we just discussed. Then we have this trade-off between heavy nuclei that have a large cross-section, but we want to have light nuclei in order to be able to have an efficient kinematic transfer, okay? And for this, well, we are going to focus on this. The noble liquids do cover all of these conditions, and also they kind of cover the conditions for the dark matter electron interactions when we are looking at low energies, okay? So why noble liquids, okay? So the reason is that many or all of these produce scintillation light. So you have a signal. So if you deposit energy into a noble liquid, it will produce light, which is not always the case with other elements, okay? And one thing that is key is that the light that is produced during scintillation has a wavelength that is not absorbed easily by the material after creation. This is also not very common, because when you have in a whatever material that scintillates is that in many times the excitations are the same in which it's easy for the material to get excited even through photons or through through ionization interactions, okay? And that is not ideal because, well, you produce a photon, but then you absorb it right away. So then you are not able to see it coming outside of the material, or you see this after a long transport of the photon inside the thing, of being absorbed and re-emitted and other stuff. So in order to solve those problems in other materials, you need to add other components to the mixture in order to shift the wavelength, and that has, of course, a lower efficiency, and yeah, that's not great. So this is completely key. Then this also translates into a relatively low energy threshold. Why? Because if you have more photons, then this means that you need to deposit a smaller amount of energy to produce a large number of photons. So you have a low energy threshold, or a relatively low energy threshold. Then this is also very important, that you can build things that are very big, because you have a lot of these materials around. You can just purify them relatively easy. The chemical purification of noble gases or noble elements is easy, so you can produce that. And you can produce them extremely pure, okay? And then you have this self-shielding characteristics that is also very important, and it's very much exploded by the many experiments, in particular xenon, is that if you have a material that is very dense and you have position resolution to know where the interaction took place, well, you can just discard whatever happens close to the edges of the detector, and the material itself is shielding the inner core of whatever of your detector from outside radiation. And we will discuss that also in detail. Then this is also a key reason, and one of the reasons why it was selected in the first hand for many experiments, that you are able to tell apart nuclear recoils and electron recoils interaction. And as I said before, if you are looking for WIMPs, that's absolutely a game changer, because most of the background is produced by electron recoil interactions. Okay, and which is very, I don't know, unexpected, is that there are two different techniques for doing this. One that is the pulse shape discrimination, that is the one that we are going to discuss first. And then the other one is exploiting the fact that the amount of light and amount of ionization that is produced in a noble liquid is different if you have a nuclear recoil or an electron recoil. And these two things happen at the same time. I mean, they are not, it's not a given, but yeah, this happens in noble liquids, okay? Well, so essentially, yeah, I'm going to move forward. And sorry, many of the slides at the beginning are boring, but we need to get to why we are using these things. So here is a list of many of the noble elements, okay, and their characteristics. So here, what is important to look at is essentially, well, remember our wish list from the beginning, that we want things that are heavy. So in that sense, we want xenon. Xenon has a lot of nucleons in the nucleus, okay? And also, it is very dense. So the self-shielding characteristic is good. You are able to produce detectors that are very massive and still fairly compact, okay? At the same time, there is the problem with the efficiency of the kinematic transfer between dark matter and the target itself, okay? In that sense, there is also krypton, argon, and neon. So we are going to consider xenon, argon, and neon for the next discussion. That are the three elements that have been mostly used for many different reasons. And essentially, this is the way to select stuff, okay? So again, the star element here is xenon because of many reasons. The first one is that the scintillation light that it produces, it has a wavelength that can be directly seen by the cheapest and most common photon detectors that are photomultiplier tubes, okay? That is amazing because that simplifies the construction of your detector a lot. You don't need to do anything to the light that is produced, okay? You just need a PMT with a window that allows UV photons to go through. That's not the case for all the other elements. For all the other elements, the light that is produced, you need to do stuff. So you need to absorb it in a different material and then re-emit it at a different wavelength in order to be seen. And that is a problem, okay? Because this reduces the amount of light that you are ultimately going to get. And then this column is also absolutely critical. Xenon, again, here shines because it has no long-lived isotopes that are radioactive. So you purify it, and as long as you are able to chemically purify it and just have xenon there, you won't have any radioactive background coming from the material of the detector itself, okay? And this is absolutely critical. That's not the case for argon. Argon has a naturally occurring radioactive isotope that is argon-39 this decays and produces gamma and radiation in your detector, and it's extremely hard to separate argon-39 from the argon-40 that is what you want in your detector. So you are going to have an irreducible background that you have to deal with inside your sensor, okay? And that is a big problem for the argon detectors. There are ways of dealing with this. One of them is just looking for sources of argon that are coming from underground. We can discuss at any point why this element is produced, but I mean, for now, there are sources of argon that are cleaner that you can get. So you can go to some mines and take argon from them, and that argon has a lower percentage of argon-39 in it, so you can do better things. There are also efforts in trying to isotopically separate argon-39 from argon-40, but this is very, very, very hard, okay? And for neon, the thing is that it doesn't matter if there are radioactive isotopes. Well, there are no radioactive isotopes of neon. And the thing is that because the vapor pressure is so low, so you need to have around 20 Kelvin in order for the neon to be liquid, all the other impurities just freeze out. So it is very clean just by the thermodynamic properties. But so this is the table. Argon turns out to be, well, the other thing here is the price, okay? And you will see that, well, this is important, especially if you are trying to build a ton scale detector, okay? So here the cost of the xenon is huge. So this gives you an idea when you are thinking about a ton scale detector that typically has tens of tons of xenon in itself. So it's 10,000 times 1,000 roughly. That's a lot.
Javier,
Okay, yes.
Is this the extraction cost or the total cost?
This is when you, just including purification, bottling, and everything. So when you go to the industry and say, okay, I want to buy xenon, they say, yeah, no problem. Yeah, $1,000, you have 1 kilo. Okay, I mean, this is a rough estimate. This is not the bulk cost, but it's ballpark. Okay, oops, yeah. Okay, so and yeah, so the other thing is that with this price tag, that is the biggest disadvantage of xenon other than the mass itself, that is a heavy nuclei, is that, well, experiments essentially look like banks, okay? You buy xenon, but then you have a stock that you can essentially sell. So there are experiments that actually have made money during the running of the experiment because they buy the xenon at the beginning and then the prices go up. And when they sell it, they actually have extra money after running. So that may be an advantage actually, yeah. So now, going into the different techniques, the simplest one is what it's called the single phase detector, and that is just a volume filled with whatever noble liquid that you select, okay? And then you have light detectors all around. So in this design, this is the simplest thing that you can do. You are essentially just looking at the scintillation light that is produced in this volume. And if you have a good design, you are able to collect the vast majority of these photons, and also by looking at the intensity of the light that you receive in each of these photosensors, you are also able to kind of reconstruct the position inside this volume, which is, again, very important if you want to fiducialize and just select the areas that are at the core of your detector and that are cleaner. Okay? In this design, there are many, many examples. I'm going to only show one example per technology, but there are many. We can discuss the details of the different efforts. This one here that looks like a Death Star, it's a 3-ton detector that it's running at Snowlab. It's called Deep 3600, okay? And all of these things are photomultiplier tubes that then are coupled into a ball that is at the center, that is this acrylic vessel, that it's filled with 3 tons of liquid argon. Okay? There are experiments using xenon instead of argon. The biggest one right now, it's called Christmas or Xmas, okay? But there are efforts using different targets. In this case, I chose argon as the example for the single-phase detector because of a very nice characteristic that is very much used as an advantage in argon versus xenon detectors, okay? Yep. Yes, it's just liquid and it's a completely homogeneous detector.
Can you repeat the question? Just.
Oh, yeah. She asked why this is called a single-phase detector, and the reason is that all the target material there is in a single phase that is liquid. Okay. In principle, you could just run this as a gaseous detector and have just gas instead of liquid. And sometimes it's done during commissioning, but the total mass it's really low. Okay. Okay. So this, what I'm going to tell you, happens both in argon and in xenon too, but with a very critical difference. So what you have when you start, it's an atom for argon or xenon, okay? And then it gets excited by some ionization, in this case, I don't know, whatever, a proton, okay? But whatever, it gets some energy. And there are two things that can happen. So it can go into an excited state directly, or it can ionize, and then coupled with another argon nucleus that it's there after it is ionized, and produce like a argon molecule, okay? And then it captures an electron from the environment, and then it gets into this state that it's called a triplet. Again, these two things, or this other path in which the argon just goes to the excited state immediately, and it can also go into this triplet or a singlet state. In both situations, what happens, I mean, it's that you end up in a molecule in an argon molecule, but these two things are in a different excitation level. So they will last different amount of time until they just dissociate and produce light. They will produce essentially the same wavelength, okay, no difference there, but the lifetime of these two states is very, very different in the case of argon. So you can have 5 nanoseconds compared to 1.5 microseconds. So we are talking orders of magnitude difference here. In xenon, there is a difference, but it's not as big. It's only a 5-fold. Okay, so we can explode this to identify nuclear recoils from electron recoils, because it turns out that nuclear recoils and electron recoils produce these two states in a different fraction. Okay, so in nuclear recoils, you pretty much produce a lot of the fast-lived ones. okay, and very little of the other states that live longer. And in electron interactions, you have that you produce a lot more of these other bounded molecules that live much, much, much longer, okay? So when you look at the signal, if you have a digitizer that is fast, in a nuclear recoil, you will just essentially see one big spike and very little after. And in an electron recoil, you will see the big spike, but then a lot of decaying grass after that. So you can use this to discriminate between a nuclear recoil and an electron recoil. And here is real data. This is from deep, okay? And what you can see here is this band, that is the electron recoil band here. And in this section here are the events that are produced by nuclear recoils, okay? So just by selecting in these two variables, you can essentially discriminate between nuclear recoils and electron recoils. And the discrimination in argon is amazing. At least it is amazing for relatively high energy. When you go to the lowest energy, as always, everything gets mushed up and you don't have any discrimination or very little discrimination. But at high energies, it looks amazing, and the discrimination is 10 to the 8th. So you don't confuse an electron recoil and a nuclear recoil event, okay? So, but you can only do this kind of amazing discrimination with argon. You can still play this game with xenon, but because of the time scales are so much closer in xenon, these two bands are essentially very, very close to each other. And there is another technique that we will discuss later that is mostly used in xenon. Yes?
Could you repeat what are you showing in this plot? I don't understand the
Yes,
the plot.
sorry. So in this plot, the x-axis here essentially is the amount of photons that are seen after an interaction, okay? So you have a particle that comes into the volume of your detector. It produces, it deposits some energy, and that produces some light. And you detect that light. So this PE, it's photoelectrons. So this here is the number of photons that you are seeing after an interaction, okay? So each vertical line corresponds to exactly the same total amount of photons, okay? And in this axis, essentially what you have is the time scale of the signal, how wide it is, okay? So, well, or the inverse of that, actually, because, yeah, sorry. But essentially, it's a measurement of how wide the signal is. So if you have things that are electron-like, okay, in this y-axis, they will be around this value because all of the spikes look the same and they are just spikes with well, sorry. In this case, the thing is that, well, in this case, okay, what you would have is just a lot of grass if it's an electron event, okay? And if it is a nuclear recoil, you won't have any of this grass. So if you look at how is the spread in time for these kind of signals, it will be much longer than when you look at the spread in time for these signals. And in this plot, sorry, they decided, this is normalized to 1, and they transform these two parameters of how time spread it is in something that goes from 0 to 1, and it's actually reversed, okay? So the ones here are the ones with the longer time, and the ones here are the ones with the shorter time, okay? Sorry, I didn't.
What about the color bar?
The color bar is the number of events that you have in each bin. So this is a 2-dimensional histogram. So the ones that have, for example, here, you have a lot of events compared to what you have here, that you have less events. Okay?
Okay, thank you.
This is the fraction of the signal, right?
Yes.
In a given time
exactly.
window.
It's a fraction of the signal. Yeah. Yep.
just to clarify, would WIMPs always cause nuclear recoils then?
Yes, I mean, at least, I mean, you need some kind of model to interpret your data. That's always the case, okay? The WIMPs, the cross-section is much, much larger for nuclear recoils than for electron recoils. So you would essentially assume that it's completely dominated by that channel. That doesn't mean that WIMPs cannot interact with electrons, but it means that the vast majority of your signal is going to come from nuclear recoils. And in a discovery search, yeah, because you are very close to the minimum number of events, they will all be nuclear recoils. Okay?
Thank you.
Okay, so moving forward. So this was the kind of the last slide for the single phase design for detectors. There is another design that was pretty much, I mean, that has many advantages and is the go-to technology for xenon detectors that essentially cannot really play this game for discriminating nuclear recoils and electron recoils, okay? So in this design, what you have is a vessel in which you have two phases. One phase that is the main phase, it's liquid, and then you have on the top a little bit of gas. The reason for doing this is that in addition to light sensors surrounding this volume, okay, you also have here, just above the surface of the liquid, a grid that has a very, very, very high electric potential. And that will produce that when you have charge that is very close to this grid, it will be extracted from the liquid and accelerated, and that in turn will produce a light signal. Okay, so this and we will see how that is used by this idea. We also have now an electric field that goes in this direction. Okay, that is different from the single phase in which the design was much, much, much simple. We didn't need to have any electric field or this super fine tuning between a grid and the liquid and other stuff. Okay, but let's say that we have an interaction here, a mu1, for example, that produces some interaction in the volume, and this thing here will produce some scintillation light. Okay, so this scintillation light, and also it will produce some amount of ionization in this position. So this scintillation light will travel very fast and be seen by your detectors. Okay, and in the bottom I'm just plotting the amount of signal seen by the overall all the sensors that you have here, okay, against time. So you get this signal that it's called S1 that is very fast, and it happens almost immediately after you have an interaction, and this is scintillation light. But now you have this electric field, so all these electrons that you ionized after the interaction, they don't recombine in place. So in a single phase detector, they will just stay in the same location, recombine and produce light later on, more light. So in a single phase detector, you actually produce more light than in this time projector or dual phase detector, because of this ionization effect that you separate and you don't let them recombine. So then, because you have this field, the electrons will start to travel to the surface, okay? And this takes a long time. You can see after your signal, they travel, but this is, I mean, they are traveling just by diffusion with this electric field. They don't travel at the speed of light, okay? So it takes a long time. But then when they get to the surface, they are extracted by this grid that, because it has very, very fine wires, it amplificates the signal. So I don't know if you've seen this in other neutrinos detectors, but what happens is that when you have an electric field in something that is extremely small, the electric field gets amplified in the proximity of this very pointy or sharp or small scale thingy, and there the field is so high that the electrons are accelerated and they collide with the other electrons, sorry, the other atoms that are in the gas there, and when they collide, this starts an avalanche, similar to what you have in a photomultiplier tube, that they multiply, 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 and they produce a lot of light. So you have here a flash of light that is actually much larger than the scintillation signal that you had there. It's like a spark, if you wish, okay? So you have then this huge signal here. And this is a very, very smart design, because having these two signals allow you to do many things. One thing is that just by looking at what's the time difference between these two signals, you can tell where this event took place, because you know what is the speed at which the electrons travel through the liquid, okay? And just by simple kinematics, you can reconstruct where it happened. So it gives you a very good spatial resolution in this vertical direction, okay? The other thing is that the size of these signals, okay, will depend on essentially how much ionization versus scintillation light was produced at the very beginning, okay? So, and this we know that it's different for nuclear recoils and electron recoils. So in xenon, even though these two states are very close in lifetime, the two states, that excited states for the xenon molecule, they are produced at very different rates depending on how much, I mean, if it's a nuclear recoil or an electron recoil, and they will produce different amount of ionizations that you are splitting at the very, very beginning of this. So you don't let this recombine, and looking at the fraction of this will allow you to have a very good separation between nuclear recoils and electron recoils. And this is the preferred technique for xenon. And we will discuss how good it is in a few slides.
I have a question.
Yes.
So do you need to have this dual phase to have the electric field?
Well, it's not just for the electric field. You need to have the avalanche, the multiplication, and for that you need a material there. And yeah, the simplest way of doing that is by having the same material as in the liquid phase, because all your optical sensors are tuned to this particular wavelength, so you want the same wavelength, and also, yeah, it's the simplest by far.
Thanks.
Okay? You don't have to worry about adding additional sources of contamination. In these experiments, you always want to minimize the amount of different elements or materials that you are using, because each of them you need to screen, clean, and stuff. In this case, it's a much simpler design. So I'm going to use xenon n-ton as the example for this technology. There are many other experiments that use dual phase TPCs. We can discuss them in the coffee break. But yeah, essentially the way most of these experiments are designed is pretty much the same. So I'm going to use this just as an example. So you start with a mountain or a lot of material, because you want to stop the cosmic radiation. The environment is, I mean, our environment is constantly bombarded by cosmic rays and radiation from outside, that the only way to stop it is to add a lot of material. The simplest way is a mountain, but you can also have these things in mines, like Snowlab. So the xenon n-ton detector is in Gran Sasso, that is in a mountain. It has 3 big holes, and xenon is located there. So you start with that. Then after that, you place your detector inside a big shield, and we are going to discuss this. And look at the scale of this thing. It's huge, okay? This is like a building size experiment. This here has 3 levels with offices and machines for purifying the xenon and keeping these things running. So this thing is huge, okay? Now, if we look at our detector from outside, we have this big tank that is the outside shield, and this has just a sign showing what's inside. This is printed there, okay? But if we look inside, after the mountain, to reduce the amount of cosmic radiation to a manageable level, we have another kind of layer, Russian doll, that is the muon Vito. That is this big water tank that is surrounding the core of the experiment where the sensor is located. So this is all filled with water, and you have here photomultiplier tubes that are looking at light, and when a muon goes through water, if it is a high energy muon, it will produce Cherenkov radiation. You already heard about this in the previous talk yesterday, okay? So that light will be seen by these 84 photomultiplier tubes that are looking in, and you will be able to tell whenever a muon goes through your system. And that is very important because muons can produce cascades and can give you other issues inside your sensor. So you use this to tag sometimes in which a muon came through, and then you beat all the data that was collected during this time window. So you have a much cleaner sample. After that, we are focusing on the inner part of this, and then there is another Russian doll layer, okay? Here you have the neutron Vito. Here it's a very similar design, okay? Inside this vessel is our TPC, but it is placed inside another volume that has gadolinium salted and water. And the reason you add this thing here, okay, is because this thing captures neutrons once they thermalize. So if you have a neutron event in your volume, it will look exactly the same as a WIMP event because it's a nuclear recoil, and you want to be able to tag those and discard them. So the way they do it is that, well, you have a neutron event, it produces a WIMP-like event inside your TPC, but then it goes outside. And outside it is captured by the gadolinium, and then it decays. And when it decays, it produces a lot of light. So essentially, you are seeing the light of these delayed neutrons, and you can also use this to veto the time windows that happened before. So you are using this as a delay veto to see whatever event you have in here, if it is a candidate for being a neutron or a WIMP-like. Yes?
So I imagine that you have like the gadolinium layer on both sides of your main detector volume, right?
Oh yeah, so this is in the center of this volume, and it's completely immersed in this liquid, yes.
So if the neutron didn't hit on the first time you went through it, like on its way towards the central volume,
Yes.
how can you make sure that it's going to hit on its way out?
So here, what you are looking for is not so much events that are coming from outside. Well, you have neutrons that are coming from outside and are seen by this, but the things that worries them, I mean, this is relatively big. So the neutrons that are traveling through this have a very high chance of being captured, I mean, thermalized and being captured in this large volume of water, okay? So going from outside without producing any interactions, it is possible, but it's very, very, very unlikely, okay? And the thing is that it needs to get in here with enough energy to produce a nuclear recoil that you can see, because also the TPCs has an energy threshold, and if the nuclear recoil is below this energy threshold, you will not see it, okay? You will discard it. And if it has enough energy to produce that, it definitely has enough energy to come outside, or not definitely, but very likely has enough energy to come outside. So you are using this mostly as a delayed tag, not so much as a pre-tag, okay? Although you can also do that. But the thing is that in this case, you are able to see neutrons that have a very, very low energy, much lower than you would be able to see inside here, okay? And you are using that to tag whatever events you happen to have inside the vessel, okay?
Thank you.
I am a little bit confused because in the previous slide we started with muon coming from outside, right?
Here?
And then in the previous,
Yes.
we started with a muon, and then we are talking about a neutron.
Yes, so I mean, all these different layers are designed to handle different types of radiation. Okay, the outside layer, this big water tank, is designed to handle cosmic radiation, in particular cosmic muons. Okay, the inner part is designed to deal with a different kind of background. Okay, the neutrons here are mostly coming from radioactive materials in the surrounding of our detector. Okay, so there you can have neutrons that are produced and they travel towards your detector, and you are trying to veto those. These are not, cosmic neutrons, but radiation that is produced inside your detector. Okay.
Thank you.
Okay, so so this is the neutron veto, that is an active veto, in the same sense that the outside water tank is an active veto for shielding muons. Both of these are built with extremely radio pure materials, so they are also a passive veto. So if you have radiation coming from outside, it will most likely be stopped by these two things also, in addition to the active vetoing. So now we finally get to the TPC, okay, that it's at the core of all this, and this is how it looks like. So you have a vessel that it needs to be a pressure vessel able to withstand having all this liquid material there that wants to be a gas. Okay, so it needs to be a high pressure vessel, and inside of this, submerged, you have here photomultiplier tubes that are on the top. Here you will create this gas pocket, okay, between the liquid and the tubes here. About this height, you have this grid, okay, that extracts the electrons and produce the second flash. And up to here, all of this will be filled with xenon. So here you have the bottom layer of PMTs, and all of this is kind of submerged in xenon. Okay, so that was a drawing. This is how it looks like. So it really looks amazing. These are all the photomultiplier tubes that are looking into the xenon volume. This is how it looks when it's closed. And all of this, it's done in a ultra clean room, okay, like we discussed yesterday. So these detectors are large, they have large volumes, so they really need to worry about radioactive contamination and radioactive background. So all of this handling, construction, cleaning, everything is done in ultra clean environments that people raise like this. After you do this, you put everything inside your detector at the core of the two other detectors that are vetoing outside or inside radiation, and then you run. So just to go back and summarize quickly the idea of the dual phase TPC. So we have two volumes, gas, liquid. An event that happens, it produces scintillation light and ionization. You will be able to see both this immediately and this delayed. So by the time of the drift of the electrons towards the surface where they produce the second flash, then you can reconstruct the position here, and by looking at which photomultiplier tubes have seen the first flash, then you also can reconstruct the other coordinate here, okay? So you have 3D reconstruction, and you have the ability to separate between nuclear recoils and electron recoils by looking at the size of these second signals compared to the size of the first signal, okay? So this is your tool set. And how does this discrimination between nuclear recoils and electron recoils look like? So here is calibration data from xenon. This was taken by xenon 10. Now we have a much larger detector, but essentially is the same. Okay, and what you have here is this distribution are events that are produced by nuclear recoils. And in the X scale here, you just have a variable that is a function of the ratio between the second signal and the first signal. Okay, so here, if the second signal is large, you have the larger second. Yes, I'm always confusing. Yes. So here you have the largest second signal, and here you have the largest. Sorry, all the other way around. Here you have the smallest second signal compared to the first one. Okay, and here you have the largest second signal compared to the first one. And although you don't get as an amazing discrimination as in the case of liquid argon, you do get pretty good discrimination. So here, for xenon 10, the rejection is 99% if you take an efficiency for the nuclear recoils of 50%. And what does this mean? So it means that if you set a cut here, okay, at about half of the distribution, or where the peak of your distribution of nuclear recoils are, and you say, I'm going to throw away all the events that have a ratio between the two, S1 and S2, that is higher than that, so I'm going to throw away half of my nuclear recoils events, okay, then the remaining half of the events will be much, much, much cleaner. And I will be able to reject 99% of the electron recoil events, okay? And this is something that is very common in dark matter experiments, that you are willing to reduce your efficiency and throw away a large fraction of your events just to get a cleaner sample, okay? Okay, so this is how it looks in 2D. So here we have the first signal and the second signal, and on the top, then the ones with the larger second signal, we have the electron recoil, and then here the nuclear recoil events. So by having a region here in which you reject all the things that have a large second signal, you are able to keep roughly 50% of your efficiency, but it is a very clean sample. Okay, this is also real data. This is coming from xenon n-ton, so the current iteration of the effort, the largest one, with many tons of liquid xenon inside. Okay, so after you run like this, okay, when they do, I mean, this is calibration data, so you have a lot of stuff here, but when they actually do run, they don't see any events in the region that they have selected for the nuclear recoils, and then they proceed to place a limit. So here, this line is the limit, the latest limit produced by xenon n-ton. So what are these plots? I know that you've seen it a lot before, but from Dario, I've heard that it would be good to discuss this a little bit with a little bit more detail. So this is essentially a plot in which the x-axis is just the mass of the candidate. So the further you go in this direction, the heavier the dark matter candidate you assume it is, okay? And remember, you have less events, so less particles that can scatter with your detector if they are more massive. And in this axis, the y-axis, is the cross-section, essentially. What is the probability of seeing it interacting with standard model particles? Okay, so what these lines mean is that, for example, if you have an event, a cross-section here that is 10 to the minus 43 and a WIMP mass of 10 MeV, you would see a rate that would be so high in your detector that you would have seen a lot of events in your detector. But if you don't see any, then you say, okay, I start lowering the cross-section until I get to a position in which I don't predict to see any in my detector, essentially. I mean, and that is this line. So what this line means is that whatever it's above it, it's rejected, because if nature was like any of the points here, you would have seen it in your detector, okay? Then moving forward. So that was the xenon n-ton result. That is not actually the best result that we currently have from TPCs, from xenon TPCs. This is just a history of what's the best cross-section for a given mass of 50 GeV. So it would be something around here, okay? What is that cross-section for different experiments? And the better the experiment, the more sensitivity is, and the lower you are able to go. Okay, so the current record it's by LC, that is also an experiment using a xenon TPC, and that is the design is pretty much the same as what I discussed before. And then the red squares here are the planned experiments for the future. All of the xenon experiments are going into a grand unification. They are all merging into one single effort to accumulate, I think it is about 1/3 of the total xenon mass available commercially in the world, which is a lot, okay, to get here. But this has not happened yet, so we are here. So this is the best result. This is the result coming from LC, okay? That is better than the result coming from xenon n-ton, that is around here. And what you have at the bottom is what we call the neutrino floor or the neutrino fog, that this essentially in the past has been seen as kind of a hard wall that it will be very difficult to improve on. These are the events that you will start having from environmental neutrinos interacting with your detector, okay? So you've heard that neutrinos can also produce interactions that pretty much mimic the ones of a WIMP or a neutron, so they will produce nuclear recoils in your detectors, and you have a flux of neutrinos that are coming from different sources. I will discuss in a little bit which sources, that will ultimately provide an unreducible background to your experiments. So once you get there, it's not a wall, because you can still keep making your detectors bigger, but it's going to be harder, because you will need to understand this background with a precision that needs to be good enough so you can subtract it and keep going. So that is not easy, because you really need to understand this background very, very precisely in order to do that. But in LHC experiments, it's done continuously. Okay, so when they are doing whatever search, they are flooded by events, and they subtract this by modeling the background and subtracting it. Okay, so the other thing is that this is the way it is typically presented, this neutrino floor, but not all the neutrino floors are born equal. So when you see these together in a plot that shows experiments that use different targets, it's actually not correct, because here in this axis, you have selected a variable that is a transformation of what you see after taking into account the material of your detector, the target material of your detector. This is translated into dark matter and nucleon cross-section, but the coherent cross-section from a neutrino will be different depending on the target. So here what you have is a very nice paper produced by Xenon, in which they plot the different neutrino floors that you expect for different experiments using different target materials. And for example, if you are using lighter things, then you expect things that are, for example, helium, you expect things that are very, very different from the neutrino floor that you expect from xenon. Okay, so when you see these plots, you always need to be aware that you need to compute your neutrino floor for the particular material of your experiment. Okay. Then let's dig a little bit also in this neutrino floor. So there are many different sources for the neutrinos that are coming into your detector. And in here, so again, in this plot, we have the WIMP mass on the x-axis and the cross-section with the nucleon on the y-axis. And the colors here reflect what's the intensity of these fluxes that you expect. What is the number of events that you expect to see from these different sources? So you have the atmospheric neutrinos, okay, but you also have reactor geoneutrinos that are coming from the environment, and all of these things will produce hotspots in which you expect to see a lot of events on, okay? But these orange regions are regions in which you will have some events already spilling from these sources. And the easiest one to see, or the one that we are closer, is this one, beryllium-8 neutrinos that are coming from the sun. And actually there is, I mean, these neutrinos have already been seen by dedicated experiments looking for this. And you've heard about this in the previous lecture. So, and the thing is that now there is a claim by Xenon that they have also seen it in their detector. Okay, so there is this. I'm not going to go into details. This was presented in IDM conference last week, but essentially what they see is that they observe an excess over the no signal hypothesis that is about 2.7 sigma. So this is not yet discovery in the sense of the 5 sigma rule, but they are starting to see a signal there. And probably LC or other experiments will definitely see this, or even Xenon Anton with longer run. So I'm out of time, so I'm going to stop here. And yeah, if any questions.
More questions to Javier? Over there.
Hello. So, in light-dark matter scattering with electron search, we usually use only S2 for dual-phase detectors. Could we also like try to search for this light-dark matter scattering with electrons in single-phase experiments?
So, I mean, it depends on the backgrounds of your experiment in your single phase. So let me comment a little bit on the question. So I didn't have time to go into a lot of detail on the light dark matter searches. So all of these slides have been focusing on the WIMP-like searches that are above 1 GeV for the dark matter mass. If you want to go to lower masses, you can do that by looking at dimmer signals that would come from interactions that produce a lot less photoelectrons there. And also, when that happens, essentially the first signal, the scintillation signal that is the smallest one, you remember, is this one, this signal at the beginning. If you have an event that is very low energy, you will not see it, okay, over the noise. You will only see the S2 signal. So when you want to go to lower energies, you have to rely on the S2 signal only. That is much, much larger than this because it has amplification when it gets to the surface, the ionization. In dual phase TPCs, there are many analyses that are done for this low energy region, looking for light dark matter candidates using S2 only signals. These are typically not background free searches, so you have some background there, and you are trying to see other stuff, like, for example, modulation or other characteristics of the events that you see. But then there, of course, you don't have any nuclear recoil, electron recoil discrimination, and also you don't have information about the C coordinate here, because you don't have this drift time. You only see the second kind of flash here. Okay, and the question was, okay, this is done for dual phase TPCs. Can you do this in single phase TPCs? And the answer is yes, but the threshold is much, much higher. Because although in single phase TPCs, the scintillation light for the first flash is bigger, it's still smaller than what you get for the second flash in here, okay? So essentially, you can do it, and I mean, people are doing this, but it's the sensitivity, it's usually, yeah, it's harder to get there.
Here, another question. Here. Okay.
There?
Yes. So usually when you talk about this neutrino fog and how to beat it, the main focus is always on directionality. But are there any other detection strategies that could maybe improve the situation to get through this previously irreducible background of neutrinos?
Not that I am aware of. So the directionality is one strategy that you can have here. So the thing is that, well, if you are looking at, if you have a detector that is able to tell you the direction in which the dark matter is coming from, then, for example, you could look in a direction where you don't have these neutrinos, or that the neutrinos that are coming from the sun, for example, well, they are coming from the sun. Okay, so if you see an event of something that is coming from a different direction, then you would be able to tell that this is not a neutrino and it's likely a dark matter event. So directionality, has been the go-to technique to go into this fog. The other thing is what I mentioned before, essentially be able to do very detailed modeling of this and have different technologies, because if you have different target materials, you will be able to say something, because the rates as seen here, okay, for the different target materials will be different for neutrinos. So you should be able to also to tell a lot about your signal if you see it with different target materials. And that is something that is, I think, general for dark matter. I don't think anybody will believe that, well, I don't think that the community will believe that we have seen dark matter without any doubt with just one signal. The same as with Dama, even if it's an experiment that it's super open and everybody is super happy about this experiment, with just one signal, I don't think that that will have the convincing power. But once you have one signal, you know where you want to put your effort, and then you start designing other experiments with different target materials, different techniques, to try to cross-check that signal and get more information also, and see if it's compatible with neutrinos, with other sources of background. Just one signal won't be enough.
Thank you.
Okay, so I suggest that we break, that we stop for coffee break now, and then remember that there is this half an hour question session later. So if you have more questions, just save it for later. And so Martin has some announcements, so we should just thank the speakers again in the morning.
Thank you. So yes, the first announcement is just a reminder of what Edivaldo just said, that we now have this discussion session at 12:30. So we'll have the 3 speakers here, and you'll be able to ask questions.
saw the analysis of LHCb for the search of dark photons decaying into a pair of muon particles. Better? Sorry. And we saw that the analysis was performed by dividing the data sample into two subsamples depending on the lifetime of the dark photon. So basically there were two data samples, one where it was possible to define a displaced vertex for these events, and the other were considered prompt, so decay immediately after the generation of a dark photon. We saw the analysis for the prompt case and the result, and we saw also which are the main backgrounds which are rebound related to the misidentification of particles as muons within the detectors. And now I want to move to the long-lived analysis, and I want to mention and to discuss in particular about the main background for this search, which I think is very interesting, because since you are asking for this particle to have a displaced vertex, basically this request helps to reduce a lot all the backgrounds which are encountered in the prompt analysis. But you have other kinds of backgrounds. For example, this one is due to the fact that you may have a photon produced in the primary vertex that cross the layers of the Velo detector, which I remind you is the most inner part of the tracking system, and then it can convert into a pair of muons, and then you may think that those muons were actually coming from the decay of a dark photon which had traveled up to the tracking detectors and then had decayed. This is very complicated background to treat, and the strategy that LHCb adopted to reduce it up to being negligible is very interesting, because what they did was basically to build a map, a three-dimensional map of what is the material budget of the inner part of the tracking detector. And they did it using other data sets where, when they selected the hadrons produced inside this detector. So reconstructing the vertexes of the origin of these hadrons, they were able to understand where they were produced, and therefore to map in a 3D scan what is the material budget of a video detector. And here you have the result. This is the profile projection of the 3D map they obtain, and as you can see how precise it is. Here is the scale, and you can see that it reproduces almost perfectly the detector. And then they use this information to define the probability that one of the dimuon events they had labeled as displaced vertexes was actually coming from the interaction of a photon inside the video detector. And in this way, they optimized a cut on this probability, and they were able to reduce this background up to negligible levels. So I think this is very, very interesting, and also proves how these vertex detectors are precise in defining the vertex of the particles.
Can you explain a little bit more the image we are seeing, because I am confused about the detector?
This one?
Yeah.
Okay, so this is a photograph of the inner part of the first, let me come to the sketch of the detector here, of the most inner part of the tracking system, which is basically surrounding the interaction point. So you have all these layers of silicons that is just like a CCD of a camera phone that register the passages of the particles and give you the information of where was passed the particle had passed, so what was the trajectory. And it is a sort of series of layers of these silicon strips, sorry, wrong way, that register the passage of a particle. And here you have one of the two halves in which the detector is divided, because you have to imagine you are surrounding the interaction point from where the two beams come, and here you have the two halves of the detector. This is the bottom one, and then you have another one, which is not in the picture now. Now it was just for showing in the picture. But here, for example, in this profile, which has been built using the reconstructed vertices from hadrons produced inside this material, you have both halves. So this is the profile of what you're seeing here, basically.
Okay, thank you.
Okay, so about the analysis of the displaced vertex, there are some striking differences compared to the prompt search. In particular, you can see that the range of masses explored is much smaller. On the lower side, this mass range is limited at 214 MeVs, and this is the same as in the prompt case, simply due to the fact that we are searching dark photon decays to 2 muon particles, and if a mass goes below 2 muon particles, you cannot decay into those particles. But on the larger mass size, the limit that you have here is due to the fact that if the dark photon becomes more massive than 350 MeV, then his average gamma factor, due to its large mass, is too low to allow it to travel enough to be detected as a displaced vertex in the detector. So this is a very limited in range search compared to the prompt analysis. But on the other side, given the fact that you are using the information from the aspect that the vertex is detached from the primary vertex, you can reduce backgrounds, and also you can have larger efficiency, releasing some cuts in the analysis. So as in the case of prompt decay, the data sample were divided into bins depending on the invariant mass measured, but now they were divided in 2 dimensions, so in bins on the invariant mass, but also on the lifetime. And each one of these bins was fitted with probability density functions that included the information about the dark photon production, all the background considered with all the uncertainties. And this allowed to obtain some values for the parameter epsilon square and some limits to place in the dark photon scenario. I say some limit because there was no observed significance for the discovery of a dark photon. That is to say, the measurement was compatible with hypothesis of no dark photon at all. So this is the result in blue about your exclusion limits. This is mass of the prime, and this is epsilon square. And so these are the two spots that you could see in the large parameter space that I showed before, and that you can see again here. So this is the final picture of the result of analysis of LHCb. This is the exclusion limit derived from the prompt decay search, and these are the two spots limited by the display detached vertex search. Now, before moving on, I just want to mention that LHCb is not only the only collider who placed important limits in this scenario. There are other cases. In particular, I just want to show here the exclusion limit from CMS, also another experiment at CERN. and also the results from Babar, that can you see here, which was an older collider experiment at SLAC in the US, which was instead an E+E- collider. So you had two beams of electron and positron colliding, and they searched as their final state the annihilation of electrons and positrons into one photon and the dark photon, where the dark photon after decays into an electron-positron pair. So at the end of the day, your final state for Babar was one photon and one electron and one positron. Instead, CMS searched for decay in the muons, as for LHCb, produced by many processes such as Higgs decays. So this is the picture for what regards the collider in the visible.
Because I think that those sky blue regions are LHCb2, and well, that's my question regarding this graph, but also why don't we increase the mass of the A prime but decrease the coupling so that we can have other searches too?
I'm not sure I understood. You mean why do not increase the mass?
Yeah.
What do you mean?
Because you are probing, in your last slide, you said you were probing for, from 214 to 350.
Yes, and this is what you see here. Sorry. Okay.
Yeah. So the question for the range of mass would be, why don't you increase the mass but maybe decrease the coupling so that you still have maybe still a long-lived particle?
Oh, I see. Well, it's a trade-off, basically. So on one side, you are limited by the lifetime of the particles, and one side you are limited by the fact that you produce too few particles, not a large number enough to detect them. So it's the fact that these regions are very small is because there you have the really right cocktail of parameters to have a particle that can be at the same time produced in a large enough number and live enough to be detected as a displaced vertex. So that's the reason. This is you have to remember that it is a logarithmic space. So even if here seems really small, the phenomenology of this particle changes a lot between maybe here and here. So here you may have particles with escape the detector, for example, and here particles that cannot be detected as a displaced vertex.
Got it. Thank you.
Okay, so before moving to thin target, I just want to mention that you cannot just you cannot only search for visible decays at colliders, but you can also search for invisible decays. And in that case, you don't have any visible final state that you can tag as the signature of dark photon production, because you have chi particles, so you have not dimuons to tag in your analysis. But what you can do in some cases is to use the so-called missing mass technique. So if you have, for example, some interaction between two colliding beams where you have a production of many particles of a standard model and a dark photon which decays invisibly, if you are able to detect and correctly reconstruct all the momenta of these particles, you can just build this quantity, which is the so-called missing mass, and this missing mass is peaked at the mass of the escaped particles. So you can build basically for all these events a spectrum of missing mass and then search for peaks defining, for example, a dark photon. This is complicated, obviously, because you have to measure all the particles produced inside within a collision. And for example, as we saw for LHCb, which is a detector which has no 4 pi coverage, so it covers only a small portion of the solid angle around the collision, is really complicated to detect all these particles. But there are some cases where this is possible, and some analyses have been performed. In particular, one case is Babar, which is the experiment that I mentioned before, also for a visible search. It was a collider that was able to set important limits also in the invisible scenario. This is due to the fact, to two main facts. The first one is that, as I said before, is an electron-positron collider. And if you produce dark photon via annihilation of electron-positron collider, you can have a final state where you have a gamma and a dark photon. So you have not many particles to detect if you want to perform your missing mass search, just to detect the single photon that is emitted from this reaction. And the second thing is that, as you can see here, the detector, which I'll describe briefly in a moment, has a barrel shape, and the interaction point is within this barrel. So you have very large angular coverage, and so you can basically be reasonably sure that if you produce something, you will probably detect it. So this was an experiment that was not optimized to search for dark photon. Actually, it was optimized to the physics of the beauty quarks, so meson with the beauty quarks, the Y. In fact, the energy in the center of mass was that of these resonances here that are made of beauty quarks, which is of order of 10 GeV. But still, this was a very good experiment to search for dark photon. The detector has a philosophy which is similar to the collider that we saw. We have the tracking part inside, so I mean, all the silicon pixel that detect the passage of particles and give you the information about the momenta and the position of passage. And also you have a calorimeter, which is in this case made of scintillating crystals. It was sodium iodide, and this was enclosed inside a magnet, so you have a magnetic field inside, allowing you to measure momenta of a particle. So they performed a search for dark photon, and what they did was to basically, as I said, perform a calculation of the missing mass and search for a peak in this spectrum of missing mass. And this is the result, the limit they excluded because they did not find any evidence for dark photon, which you can see for large masses is still the most competitive limit that we have in the dark photon invisible decay scenario. It is interesting to note the shape of this exclusion limit. We saw for LHCb, for example, that the limit is very irregular. This is due to the fact that the invariant mass spectrum was divided in beams depending on the sensitivity of experiment as a fit, and a fit was performed for each of these beams. This was done also for Babar, but due to the resolution of the detector and the mass of the dark photon, which is considerably light with respect to the center of mass energy of the detector, the resolution is such that this here is a single beam of analysis. So Babar was not sensitive to the mass of the dark photon from 1 to 100 GeV. It was a single analysis in all of this missing mass spectrum. And this is the reason why this limit here is flat, and also the reason why collider typically are more well suited to explore for larger masses. This is also the reason why we are built. They are built to create new particles with, in general, large masses with respect to a fixed target experiment. Okay, so we come finally to the end of our this description of collider experiment in this field, and we move to the fixed target experiment. So what we saw is that collider feature important sensitivity in the large mass part, and this is due in particular to the large square root of S they can achieve. It is to say, the energy in the center of mass that a collider can achieve is very large. This is due to the fact that if you have two beams colliding with each energy E beam, the total energy available in the center of mass is obviously 2 times the energy of the beam. While instead, if you have a single beam impinging on a fixed target, that's not more the case. And the square root of S of energy available in the center of mass depends, scales at the square root of energy. So it's complicated to produce very massive particles of fixed target experiment. But since now we are thinking of a scenario where the masses of the particles, of dark matter particles, are very small, maybe not necessary to have this large center of mass energy, and it's better to stick with a high intensity experiment to search for rare events instead of a very large energy collider. So this is a bit of a change of paradigm from what is called the energy frontier, so raising the energy of the colliders and the square root of S to build very massive particles, to the so-called intensity frontier, so the luminosity of the experiment, the number of particles on target and interaction that you have. And this is the reason why you can search for these scenarios even with small-scale experiment with fixed target, as we will see from now on. So a typical fixed target experiment searching for light dark matter can be schematized like that. So how do you produce dark matter at a fixed target? Well, dark photon is basically, as we said, a photon from the kinematic point of view. So you can produce it in the same way that you could produce a standard model photon. So for example, from a radiative process that in this case is usually called a Strahlung to recall the Bremsstrahlung process. So you have, for example, an electron beam. It impinges on a thin target. You have this radiative process, so you produce your dark photon. And then, if, for example, you are in the visible decay scenario, this dark photon can decay into a pair of electron and positron. Here, we are assuming electron and positron are not muons, because now we are considering a range of mass which is below 2 mass of muons. So this is the signature for this decay. Here you have some values. For example, for what is the characteristic dimension of the angles of the two electron and positrons, which you can see depends on the energy of the beam. It can be very small, order of milliradians, and also the fact that due to this process in general, you can assume that the dark photon takes most of the energy of the beam in this process. So you end with a dark photon which has almost all the energy of the beam, and then you can try to detect its decay product, both searching from an invariant mass spectrum, as in the case of LHCb, but also searching for a displaced vertex, as in LHCb, but now with a fixed target experiment. And this is the case of the first experiment we are going to talk about, which is HPS, which stands for the heavy photon search experiment. Heavy photon is just another name that was given mainly in the past to the dark photon particle. So this is basically a very compact spectrometer which aims to both detect displaced vertices produced by the decay of dark photons produced in a thin target where electron beam impinges, and also a peak in an invariant mass spectrum from the detection of the two electron and positron inside an electromagnetic calorimeter. The ranges of energy for such experiment are fairly low compared to the collider energy, so we're talking about energies between 2 and 4 GeV. We have a thin tungsten target in this case, where the A' Strahlung reaction occurs. And then you have a silicon vertex tracker and a calorimeter made of lead tungstate, which is an inorganic scintillating material, to detect the displaced vertex and a search for invariant mass peak. So from a point of view of tracking, you can think basically of, from a functioning point of view, of what we saw for LHCb. So detectors that, which are able to reconstruct the passage of particle, their position. And since you have a magnet where all this system is enclosed, your particle will curve and you will determine their momentum. So here there are, I mean, as I said, the two distinct strategy of search for HPS. The first one, the resonance search. So here this is a simulation, that's not real data. Unfortunately, a simulation where some signal fake was injected. Here is an example of what to expect for a missing, for an invariant mass spectrum, where you have all this flat distribution, which is given by all standard model processes that can result themselves in an electron and a positron inside the calorimeter, because obviously there are many processes that can produce such particles, and this is your very smooth background. And on top of that, if you have a dark photon, you would see it as a very small bump within this distribution. This is, I mean, to be able to be sensitive to such bump, this is very complicated because you have to control very well all your backgrounds and the stability of the detector. So this is very difficult to achieve low epsilon value. So we can say that the main discovery potential of HPS is the displaced vertex detection. So due to the tracking, you can basically, again, this is simulation again, this is simulation, not real data. You can build a distribution of reconstructed vertex position with respect, for example, to the target. And here is how it is distributed, your standard model background. And if you have some long-lived particles, such as a dark photon, it would distribute like that. You would have a tail that you can analyze with statistical method to define the discovery of a dark photon or put some limits. Before going a bit more into detail about the technology of HPS, I want to say a few words about the laboratory and the accelerator that HPS is making use of, which is the Jefferson National Laboratory at the United States, in Virginia, also called JLab. This is a medium-sized nuclear physics experiment in the US, and it makes use of this CBAF, which is the Continuous Electron Beam Accelerator Facility, which is the accelerator itself. It is not a circular shape, but it's an oval because it's composed by two parts which are linear, that accelerate the electron beam, and two curved parts which just allows for the trajectory to bend and to reach the other linear section. So particles can make several passes within this system, and for each passes, for each turn they complete within the accelerator, they gain 2.2 GeV of energy. They can do it up to 5.5 passes to reach an energy of about 12 GeV. And then these particles are basically distributed to 3 experimental holes at the same time, which can operate simultaneously, where the different experiments of Jefferson Lab are located. So HPS is located in what is called the hole B, which is the central one here. As you can see, these are the rooftops of the hole. And one of the particularities of this beam is that it is basically continuous. So in general, particle beams have a time structure, such as you have bumps. You have moments where you have the passage of particles, then nothing, then another spill of particles, and so on. In that case, due to the very high frequency of operation, the beam is basically continuous. It's like having a continuous current of particle flowing to your experiment. And in the case of HPS, this current is of about 100 nanoamps, so significant current. Also, it is a very high quality beam from the point of view of the shape of the beam, because a particle beam may have a large profile, and in this case the beam spot is very focused in lower than 50 microns vertical acceptance, and also is very stable, so its average position in a vertical position is very stable, less than 30 microns. I'm talking about a vertical position, which is the one interesting for HPS. And the reason is because the tracking system of HPS has to detect very low angles, which are the aperture angles of the two electron and positron emitted by the dark photon decay. And since this angle, due to the masses and the energies in play, is very low, you have to be able to place the tracking detector, which are these strips here, so we detect the passage of the particles, very close to the beam. And since these are very delicate sensors, you cannot just place them in the beam. You have to be careful and be sure that you can go close up to a certain level, but the particle on the beam don't hit directly the sensor, otherwise they would damage it. And this is possible given the very high quality of the beam provided by Jefferson Lab. So, a bit more in particular in detail about the design of this silicon vertex tracker. So it's made by 6 layers. This was the original design. Now they added one more for more resolution, but that does not change the idea. And it has an acceptance which goes down to 50 millirad, which means that you are close up to 0.5 millimeter from the axis of the beam. The detector is split into halves. As I said, you need to get close to the beam, and now what we've done is that the detector has the upper part is lowered towards the beam, and the lower part is raised toward the beam, so to get the most solid angle covering. And you have that resolution for each layer of about 6 microns in the vertical plane. Here I have a picture of this detector, the silicon strip. So this is the active part, basically. And you have also all the electronics that are responsible for the readout and data acquisition and amplification and so on. There are obviously precision actuators to define the position of this detector, because you want to be sure, as I said, not to place it inside the beam and to destroy them. And so there is a quite complicated procedure to operate this experiment. So you have to perform scans of the beam profile, then you do the scans with the detector itself, you progressively make them closer to the beam up to the operating position. Here, for example, we have some results from the scan of the beam shape in correspondence of the silicon vertex trackers of HPS. So this is there are some detectors along the beam line that basically measure the distribution of the particle of the beam with respect to the axis of the beam itself. So you have this different detector, which is called beam position monitors, and there are many. This is one of them, which is placed just in front of the XPS experiment, and these are used to understand if the beam quality, the beam tuning is fine enough to proceed with the lowering of the silicon vertex tracker in the correct position. And this is control is performed continuously, because it may be that for some reason the beam steers and changes its direction and hits the silicon vertex. So this control has been done continuously, and to be sure that nothing wrong is going on. Here you can see the resolution, which is sorry, resolution, the spread of the beam, which is better in the y direction, which is interesting from important from HPS, since, as I said, the silicon vectors come from the top, from the bottom, and this is the y. But still, we are talking about really a small beam spot. And here you have a wide position scan, which is a sub-detector of the HPS silicon vertex detector, which can itself measure the profile of the beam without having to put the silicon itself inside the beam. So it's like a small wire that you pass through the beam, and depending on the number of particles that hit this wire, you see a signal which is larger and lower. So you make some points, and you have a profile, and you can define with if the width of the beam at the position of the SVT layer is good or not for your operation. Okay, so that was for the SVT. We now come to the electromagnetic calorimeter part. So this is important both for the bump hunt search, but also for the trigger. In fact, the trigger to this experiment is given by the electromagnetic calorimeter. So when you see an electron and one positron, so the position of energy into two parts of the calorimeter, you can trigger an event. So how it is produced, how it is designed, the calorimeter? As I said, are lead tungstate crystal. We should be a 4 and not a 0, sorry. And they are divided into two halves on top of the bottom of the beam. This is due also to the fact that, as I said before, you have a magnetic field before, which is bending particles. So you have basically different energy particles bended all throughout this hole here. So you cannot just put crystal there, otherwise the radiation damage would kill them. And it has 442 crystals in total, which a dimension of almost 1 centimeter per 1 centimeter, about 1 centimeter per 1 centimeter, and 16 centimeters long. There is also, which is interesting, a custom LED monitoring system that works as a calibration point for your calorimeter. So as we will see later, what may happen is that due to radiation, due to the high intensity of particles impinging on these crystals, the crystals get damaged. What does this mean? This means that they does not transmit light as good as they were in their origin, as they were new. So you may see lower signal, thinking that it's a lower energy signal, but instead it's just the crystal that is not transmitting light in a good way. So you basically recalibrate this, just impulsing some LED light inside each one of the crystals, and if you trust the LED to be stable during time, you can recalibrate your crystals, your calorimeter, and account for variation due to the transparency of this crystal. Also, there is a cooling system, because all the electronics and the acquisition, the light detection amplification have a dependency on temperature. So there is a cooling system that allows the calorimeter to be thermostated at about 0.1 Celsius degree. You have a picture of one of the layers where you have one crystal. You can see here it's transparent. It is how it should be as it is new, so like glass basically. And here you have a measurement of the performance of this detector. So what I mean with this performance, basically the energy resolution. So if an electron impinges on this detector with such an energy, what is the response of your detector, and what is the resolution of this measurement? How it is done? This is done using a particular characteristics of events, which is elastic scatter of electron of a beam inside the target. So you have your 2 GeV, 4 GeV, 1 GeV electron impinging on the target. It can many things can happen. It can also happen that interact elastically with the nuclei of the target, which means that electron changes their momentum, but they don't change their total energy. So the energy is the initial energy of the beam, but the direction is different, so that it hit the calorimeter in different position, and you can use this signal, since you know the energy of the beam, to calibrate your detector, to measure the resolution of your detector. If, for example, is a peak of energy measured with an energy beam of about 1.1 GeV. And here, if you repeat these things many times and you perform a fit to these signals at different beam energy, you can evaluate your resolution with respect to the energy. And as you can see, it follows with shape here, which is typical for electromagnetic calorimeter. Usually the resolution for electromagnetic calorimeters is defined by 3 terms, which are due to different possibilities, different happenings in the process of depositing energy in a calorimeter. So this is a relative resolution, so the sigma E over E, and this is composed by 3 pieces, 3 terms, which has been measured and has been obtained by a fit to this point. And these are the first one, this is called the electronic noise term, so which is a term that goes down with the inverse of the energy, which is due usually to electronic noise in your detector. Then you have a term which goes down as the inverse of the square root of the energy of the beam, which in general is due and attributed to fluctuation in the statistic of the shower, so it may be different number of particles produced, and also statistical fluctuation in the number of photons produced for your light detector, which follows a Poissonian distribution, so it's like it has its own statistic and its own fluctuation. And finally, you have a constant term of the resolution, which is usually attributed to leakage, that is to say that your detector is not fully containing the particle that is impinging on it, and some of this energy is escaping, and sometimes is more, sometimes is less, and this results in contribution to the resolution of the detector. And so these are the numbers fitted for this calorimeter, which is really reasonable for the type of detector and in agreement with the requirements for this experiment. Okay, before moving on, I want to come back to what I said before about the reason why you need LEDs to recalibrate this kind of detector. So this plot here shows for each crystal of the calorimeter the ratio between the amplitude of the signal caused by a light pulse produced by a LED in the crystal before and after 70 hours of exposure to the beam in the nominal operational intensity of HPS. So basically, where you see red, it means that there are fluctuations and the signal from LED is larger after the beam than before, and when you see blue, it means that the signal from the LED is lower after the exposure to the beam. And what you can see here, that the fluctuation around all the calorimeter are quite reasonable. I'm talking about 5 per mil, so nothing relevant here. But there is some region around this hole here of ECAL where already after 70 hours of data taking, you have that the LED signal is lower of a few percent even. This means that the radiation that impinged on these crystals here was so large that in 70 hours reduced the transparency of the crystals. And so you already have an appreciable effect. And this is reasonable that happens around this hole here, because here is basically where the beam passes if it does not interact with the target, so it crosses the target without interaction. So this is interesting. It is something that in such an experiment has to be considered carefully and corrected in the analysis phase. Still one slide on the calorimeter, because as I said, is used in the definition of what is the trigger of the experiment. So you are searching for electron-positron pairs. You know that they are emitted from the decay of a particle. So you are searching for the decay of a particle. So you may define the condition for example, the heating position of the particle in the calorimeters, which are in agreement with the origin of the decay from a dark photon or not. So what is done is that you require energetic cluster, which is to say an ensemble of crystal close to each other that show a significant amount of energy, which is done due to the interaction of an electron or positron, and they has to be displaced horizontally in the opposite direction from the center line of the unbent beam, according to their energies. But obviously, if you have lower energy particles where they cross the magnetic field, where they bend more, and so you have to take into account this. And at the end of the day, combining the energy measured and the impact position, and therefore the angle with respect to the center line, you can build online a trigger which is quite efficient and allow you to save only interesting, let's say, events for your search. I did not mention it before, but I think, I mean, maybe it was obvious, but I will say it again. So if you look at this picture with the perspective of the incoming beam before the target, the center of the target is here. But this hole is here, is slightly displaced from the center because we have a magnetic field, and so the majority of the particles, when the beam does not interact in the target, are bent in this location, which is not symmetric with respect to the calorimeter, not with respect to the target. Okay, so what are the main background for this search? All the standard model processes that can result in the same signature for the experiment. So a radiative process, so where you have a radiation of a virtual photon which decays into electron and positron. So the signature in that case would be basically the same because you have two clusters in the calorimeter and also the two tracks in the silicon vertex tracker. But also a bit more fancier process, which is called Bethe-Eitler, that results basically in the same final state. So 3 electrons that may impinge on your calorimeter. But there is a difference between these two, because if you look at the distribution of the energy of electron and positron produced by these two processes, so in this case and in this case, you can see that while the radiative process is distributed, obviously they took almost all the energy of the beam, because this is a sort of Bremsstrahlung, as in the case of the dark photon production. This is very similar to what you expect from the signal, so it's not, it cannot be reduced. While this one results in lower energy electron-positron pairs, which are distributed here, and therefore we are more able to reject this kind of event in analysis, during the analysis. Okay, so what's the status of HPS? HPS is basically has performed a sort of commissioning with several engineering runs, which are used to optimize all the parameters of the experiment. And they performed a final engineering run in 2016, and they published some first limit obtained from the bump-hunt search. So here you have the obtained invariant mass spectrum in this search. They search for bump-hunt, for bumps, peaks, we did not find them. And here, instead, you have the result of a displaced vertex search. Here on the X you have invariant mass, and here the vertex which is measured. Here you have the background, basically, and here is your approximated signal window. but for this statistic, it was not enough to set limits using this technology, this technique of displaced vertex. So we set limits only using the bump hunt. And these are the result. This was just an engineering run, so not really data taking complete data taking from the experiment. And they were able to place this limit here, which being a search for a bump hunt, so a peak in invariant mass, is similar to the shape of the searches which I described before, for example, for the colliders. And this instead is the projection for the displaced self vertex as soon as HPS will be able to collect the statistics that has been defined by the collaboration. And you can see that using a technique which is similar to what LHCbC did for the displaced vertex, so searching for displaced search vertex, the explorable regional parameter space is closed. And it is very interesting because it is just in the middle of it, which is the thermal target, so the regional parameter space that could explain dark matter in the hypothesis of thermal origin of dark matter. So this was all for HPS. Now we'll change a bit physics scenario, because I want to talk to you for a few minutes about an experiment, which is a nuclear physics experiment, which you may think does anything to do with does not have anything to do with dark matter, but that's not the case. So I want to talk to you about the atom key experiment, which is an experiment in Hungary, and the aim of this experiment is to study the angular correlation between electron and positron pairs produced by internal pair conversion in the de-excitation of excited beryllium-8 nuclei. So what it is, all this weird thing, I will discuss it. So what they did is to have a lithium target, sorry. They made a proton beam with order 1 MeV mass energy impinge on this target. And from this reaction of impinging, talking of very small energy, with really nuclear physics, so very small if compared to what we were talking before, they excite a state of a beryllium-8. So like the proton is capturing, is being captured by the lithium, you have the beryllium produced in excited state, which is to say it has to de-excite to go to the standard beryllium state we know, and this is stable. Beryllium-8. So then what happens is from the de-excitation of these excited states, two electrons, an electron and positrons are produced, and in this experiment they want to measure the energy as a V angle and the angle of emission of these particles. So this is due for nuclear physics reasons, so I won't go into detail here. But they have a detector surrounding the target, which is made of plastic scintillator, and again, some kind of trackings, which in this case is a bit different, but again, what does it to measure the impinging position of the particle. And so when you have an electron and positron exiting from your target, you can measure both their angle of emission and their energy. So here a bit more in detail, these are the states, the excited states of beryllium-8, so the states that they can produce with this very low energy proton beam impinging of this lithium target. And so you produce two excited states depending on the energy of the beam you use. You can go 1 MeV or 0.4 MeV, and you do two different excited states of these nuclei, and then they decay to the ground state of beryllium-8. Here is the cross-section for this reaction of the proton beam impinging on this lithium target, which has a spike in correspondence of the two energy used to excite this level. So why I'm talking about this? Because while we were searching for other things, we were studying the angular distribution of these two emitted electron and positron, they plotted the opening angle of the electron and positron and they saw a weird bump feature, which we were not expecting, because in this kind of nuclear reaction, you expect to have a very flat distribution. So what we did as soon as they saw this weird feature is to try to think if this could have been explained introducing a new particle which decays in a couple pair of electron and positron, which can give rise to this bump here. So the picture that they imagined is this one. So you have the proton beam impinging on beryllium target, you excite the beryllium-8 state, then from the de-excitation, instead of producing a photon, you produce some resonance, some new particles, which then decay to electron and positron pair. So here the idea is very simple. They thought, well, this is coupled to photons, is coupled to electron and positrons, this is maybe a dark photon. So they thought we discovered dark photon. We did not say we discovered dark photon, but they published a paper where they saw possible evidence of a new particles decaying to electron and positron pair. And given the fact that they know the energy of this excited state and they measure the energy of the electron and positron pair, they know quite reasonably the mass of these hypothetical particles. So at first glance, really no one cared about this result because they consider some nuclear physics weird thing, and it's still possible that this bump here is due to nuclear physics effect, which has not been studied yet. But they went on and performed other measurements using also other nuclei and changing also the detector. And they kept seeing this weird shape in the opening angle distribution of the particles. So they performed an experiment with a new detector. This is the photograph of the new one with this detector here with the plastic scintillator and the tracking detector to detect the position of the impinging of electron and positron. And here is the comparison between the plots obtained for the angular distribution with the old new setup, which is really consistent. And they went on and they performed the same measurement with an excited helium nuclei, and they also obtained the same signature. I think they did also with carbon, and they published in the last period. So again, this is something we don't know what it is. It may be just some nuclear artifacts, some artifacts due to their analysis, to their detectors, but still the interest in this thing is raising a bit. It's raising a bit because if you look at the region of a parameter space that in terms of dark photon candidate could explain that bump in the angular distribution, so via atomic collaboration, this is a region where there's still some parameter space free and free to explore. And this parameter space, you see the zoom, is very difficult to explore because you have a particle that still you can produce a reasonable way because you're not in the very low region, in the low region for the epsilon coupling, but it's still very short-lived. So it's complicated. It's a region which is a boundary between the collider, fixed target experiment, thin target, and as we will see, bin dumps. So something that has raised some interest in the community, and since I have no time, we will see tomorrow that there is one experiment which has been designed really on the fly. I have to say it's an old experiment that is being converted to this search to try to see if this is really a new particle, so searching it from the point of view of particle physics and not nuclear physics, or if it's just another illusion from the point of view of dark matter. So I think that I can stop here since I have 1 minute, and we will see the rest tomorrow.
Thanks, Luca. So I think we can jump to the general questions, yeah, and for all the speakers, but of course, Luca. So, yeah, I see Daniel here. Javier is there. Oh, there's one here.
Thank you for your talk. I am not sure who would answer my question, but if a direct detection experiment sees a signal that could be dark matter, how would the accelerator experiments react to it? Like, is there a way to probe like specific, like the probable mass or something like that?
Well, as it was said yesterday by Javier, you really need a model to make comparison. So if you don't make a model, it's impossible to make the two worlds to speak to each other. So for example, if you see a signal in an experiment which is searching for WIMPs, and therefore it has a sensitivity that can explore some region in the WIMP parameter space, you will probably be reasonably sure that the discovered particle has mass larger than something. So you may try to search it, for example, at colliders when you can achieve that large energy. On the other side, it would be complicated to the opposite. One important thing to remember about the searches at collider and accelerator is that you search for candidates, not for dark matter. So if you see a signal, for example, for this, let's say that tomorrow we discover this new particle, which is the dark photon, you probably have discovered only a new mediator, but you don't know this is the portal to dark matter, if it's a portal to a dark sector of particle which is not dark matter because it's not making the 85% mass of the universe, and so on. So it's really model dependent, and I think that at the end of the day, while colliders can give, what can I say, can explore these theories and find something new, so beyond the standard model, still you will not be sure that it's dark matter. And on the other side, we need to have the answer from direct search. So this is the reason why it's important that the research to go down in mass, for example, go on in direct searches, and so on.
Thank you.
Do you want to complement this, Daniel? Or no? No? As you wish.
No, I mean, I think that is the right answer. If you have a new light dark matter particle with some new mediator, I mean, you do want to separate out the dark matter particle and the mediator itself. So accelerator experiments will be important for disentangling those two effects, so that you sort of have some idea of where to take, in which directions the next, accelerator facilities and collider experiments and beamed up facilities. But yeah, I think Luca basically covered it right.
Since I have the microphone, I would like to ask a question to Dan. So you had a plot where you have shown these two regions of interest. So you had time in the x-axis and like detection in PMT.
Yeah, for the waveform for the CSI-7s?
For sevens incoherent, yes. So that plot is like, it's for each pulse. For each pulse, you can check at the arrival time of the signal and do a plot like that.
Yeah, that's absolutely right. And there are some pulses from just background scintillation in the crystal, basically just afterglow, long-lived scintillation lifetimes. So that's a thing that you'll always have to deal with. If you see an actual physics event, which can happen anywhere in your waveform, you'll basically see a cluster of pulses, and you'll reconstruct that cluster by finding the first pulse in the cluster. And depending on where that is, that basically reconstructs your timing, decides on whether the event lives in your coincidence ROI for measuring the neutrino interactions, or the anti-coincidence for getting the background.
Thanks. So you have like a connection to the beam itself, or you know exactly.
Absolutely. Yeah, we have a little pulse coming in from the beam saying like this is when the protons were supposed to be in the target, and then
about a microsecond later is like, yes, we actually did put some protons on that target. Yeah.
Thanks.
This is like an open question. It's more out of curiosity, like when you are colliding the beams, so you are taking data, and for how long? And does, even though this is a collimated beam and everything, does it kind of not bend but shift a bit during the data taking? And if so, when do you decide like to stop the data taking to again put it both beams again in shift?
You mean you were speaking about HPS or collider?
The collider.
The collider. So the collider actually are controlled to a very fine level. I have my experiences on CERN, and basically you have a very incredible level of control of the impact position of the two beams. You have to imagine, and this is not very intuitive, but let me see if can I go back to the slide. There was an aerial picture of CERN, but so actually what happens when CERN is operated, when LHC is operated, sorry, is that you have the protons that goes inside the collider in the two directions, that are provided by a smaller accelerator, which is as you can see here, this small ring here, which is called SPS, super proton synchrotron, and the protons to the super proton synchrotron comes from another smaller accelerator. So what happens is that at some points during the day when you are taking data at LHC, there is the so-called filling. So you put particles from the SPS to the LHC, and this lasts about half an hour, okay? And then the LHC is filled with protons to its max level, as you can say, and then they make the collision to start by changing the magnets, okay? So until the beam is degraded, so these collisions go on and go on, also maybe collision with the pipes itself, they degrade it, they go on without any other filling. So they have the same protons turning and turning again inside the collider. And this last, the record I think was a few days. So they can go on. They're so precise in bending the beam and making it follow the trajectory of the accelerator that can go on for several hours without having to refill this ring with these protons. So I think I can answer that the control is very high level, and you decide to stop and to make another fill simply when you don't have any more particles, or the number of particles goes below such a level that it's not more convenient to go on, because the number of interaction decreases up to the level when it's better to do a refill. So you activate the SPS. Actually, SPS works on its own for other experiments, as we will see. But you ask the SPS to provide another filling of protons, for LHC.
Okay, thank you.
Okay. I think I will go first, or he go first. Okay, sorry. So Javier showed us a plot where like the experiments using xenon are start to increase, and you mentioned that we will have a point that we are going to use like 1/3 of the accessible xenon in the world, right? And do you know if about like the same statistics for argon, for example? I know that Dune is going to use a lot of argon, and we have a lot of argon experiments as well. So do you know like how much argon left?
Yeah, for argon, it's not a big problem because argon is used, well, first of all, it's a lot easier to get argon. So if you are just going to use argon for industrial applications, you get it from the atmosphere. So you don't need to mine it. It's a lot easier to get and a lot cheaper, and it's very, very abundant around us. Also, there are a lot of industrial applications that use argon, so the production scale is huge. I mean, for welding and for many processes that require, I mean, environments that do not react, argon is used. So it's not going to be a problem. What is a lot more difficult is to get argon without this radioactive isotope that is argon-39. And essentially, well, the only user for that is dark matter searches. So all that argon is coming from these very few sources. So essentially all the argon that is depleted in argon-39 is being used by the dark matter community. For Dune, I mean, it depends on which of the analysis and projects within Dune you are considering, but you don't need this highly depleted argon because you have the beam signal there, so you don't need especially very, very low background for most of the analysis. So it's not going to be a problem for that, but yes, for the dark matter searches in which you really need this argon that is depleted, then it's 100% of the production, and even new facilities are being built to produce more of this depleted argon or to separate isotopically the radioactive component. And so that, I mean, there is the distillation column that is being project in Italy that is huge. It's 100 meters or more of distillation column just to be able to skim this radioactive component. Yeah.
Okay, thank you.
About that experiment of using beryllium, that 17 megaelectrovolt emission is something special about beryllium. Didn't anyone try using other atom, or the emission is something that we expect from beryllium, but no other experiment?
They were studying beryllium from other purposes other than dark matter, and so they discovered, I mean, they observed this anomaly first on beryllium, but yeah, they did it also the test on other nuclei. So they did it on helium and I think on carbon now. So and also they saw it on a coherent nuclear resonance, which is I mean, I won't explain here, but so we're going on with our studies on this effect, on this anomaly, and it is an interesting puzzle. I mean, even if not from the point of view of dark matter, if you don't believe that it is reasonable that it's dark matter, it's something that is interesting to study. I think that, as we will see tomorrow, having an experiment or few experiments that exclude the possibility that is a dark photon or something similar from the point of view of particle physics and not point of view of nuclear physics, where you have a lot of uncertainties due to the processes that really you don't know at a higher level what happens within the nucleus. So it's really something that has to be, I think, has to be done, interesting to be done, and for sure it will be done in the next few years. But yeah, it has been done already in other nuclei.
Okay, thank you.
More questions?
Thank you. So this is a question for both Javier and Daniel. We have heard about the neutrino fog or floor as a kind of bad thing, but isn't it a good opportunity to study neutrino physics?
Yeah, for sure. I mean, Someone's background is someone else's signal. So yes.
Yeah. I mean, I study sevens. I very much like the physics connected with it. One of the things that you really want to understand is, is the sevens cross-section the same for all flavors? That connects up with all sorts of NSI scenarios. The typical way to study sevens with man-made sources is with reactors and PIDAR beams. That gives you nu bar and nu mu / nu e / nu mu bar. You're missing nu taus out of the picture entirely, which are in the solar neutrino flux. So this is just a brilliant opportunity for Xenon N-Ton and Penda-X, which released this morning. Some observation of the 7 signal coming from solar neutrinos is actually going to do very complementary measurements and constraints compared to the man-made sources that we have. So yes, the information coming out of the dark matter experiments is very interesting for us as neutrino physicists.
Okay.
Yep.
Thank you. So I actually have another question for Luca now, if I may. But this one is for Luca. So about the atom key experiment, so has it been cross-checked, or is it too hard to cross-check? Do you know?
Well, it is not yet being cross-checked. There are several efforts going on. There are few, I say, human issues going on that side, because what happens in these cases is that maybe repeating the measurement requires a lot of effort. So you have to have money, manpower, and decide that you have to give your time to this search. And yet, at the end of the day, if you do it and you see the same thing, you will only be the second one to have seen the same thing. So repeating the measurement in another way, so with an accelerator, for example, to not repeating the measurement, but exploring the parameter space of that resonance, if it's a resonance, is a different thing, because it's another measurement, and there is some effort in that direction. There is an effort also in the direction of repeating the same exact measurement, maybe with some different detector. But I think this is going a bit more slowly. I know there is an effort in Italy, for example, but also this, at least I can speak from what happens in Italy, this is a nuclear physics technology, so low energy technology. And the outcome is not a nuclear physics outcome. It's another sector of physics, which is dark matter, beyond standard model. What happens often is that laboratories that do nuclear physics, they want to stick to do nuclear physics. They have their own program. Maybe they don't believe this thing. They just think it's some... I think that is similar somehow, not similar, it's different case, but there is some, how can I say, human component, as in the case of Dama. So from it will be reasonable to repeat things, to be open about things, to go on and to solve these doubts and to understand, but there are some human components that maybe slow the process, even if I'm sure that sooner or later it will be redone. Also because it's not a really complicated experiment, but still these people at Atomkey, they do it. I mean, having done this from years, they know how to do it. So it's really a matter of precise know-how. I've been involved a little in this effort in Italy that I was mentioning, and I know that is no joke. I mean, you have to really, you need some effort, human effort and money to do it. So it will be done, but with the right time scale.
Thank you.
Thank you for the lectures. Just was wondering in the search for the dark photon, if has been considered another channels such quantum like a scattering, photon, electron going to dark photon, electron. I don't know if it is constrained for some reason or.
I don't understand the channel you are mentioning. So you said are decay channels, or I don't.
Now, photon and electron, going to dark photon and electron to the final state.
Photon, electron.
Going to dark photon, electron.
Going to dark photon, electron. That is not available, not permitted, I think.
Why?
If I understood. Because you mentioned a vertex where you have an electron, a photon, and a dark photon, right?
Yeah, dark photon and the final state with electron.
But then so the dark photon is an internal line.
Now the dark photon is in the final state because you can actually measure the using the missing energy technique.
Okay.
I think, for example, you can put like a calorimeter or something and see how is the final state of the electron or.
Okay, we will talk about missing energy for sure in the last day, and maybe we can discuss with this with a piece of paper, which is which is better. You can show me what you mean.
It's like a scattering. Yeah.
Ah, okay. So sorry, I don't understand. Yeah, but I mean, from the point of view of missing energy, is much better to use the radiation processes like that, because the high energy that you are considering, the dominant, we see that it's not the only one, but one of the dominant production channel is the radiative one. So even for a missing energy experiment, which we will see an A64, for example, relies on that process.
Okay, thank you.
My question is regarding the alpha D coupling. Is there any running? I mean, through the randomization scale?
So you mean if there are bounds on the alpha D on the normalization scale? So this is so the variation in the alpha D parameter. So I don't even see you, so don't know what from the. Sorry. Okay. But can you hear me? Right? Yeah. So you mentioned. Can you hear me now? For maybe it was. Okay. So you mentioned if there is running of the alpha D constant from the renormalization scale. Yeah, probably, yeah. But I mean, I want to stress that. I mean, from the point of view of phenomenology at this energy scale, really the important thing is you see, for example, the scenario that I show fix the value to alpha of, for example, to 0, 1, okay? But this is just an arbitrary choice. There are some limits, I think, from cosmology, for example, but this is just the important thing for all the phenomena from the point of view accelerator is that you have two couplings, standard model dark matter, which is epsilon, and alpha dark, which is inside the dark sector, and one is much smaller than the other. So this basically limitates and defines the phenomenology on a reasonable level. Then, yeah, for sure there is running for dark too, but you can think of many more. This is just a toy model. You can think of many more complex thing. We wonder where does the mass of Chi particles come from? If there is a dark sector, a dark Higgs mechanism, all whatever you want. So that's it.
So we have time for one last question.
So while people think about the last question, just announcement or comment. If you didn't sign up the sheet, okay, great. If someone didn't sign up the sheet yet, please do so before leaving the room, after we get rid of it, so don't forget. And yes, today, just a reminder, we start at 2:30, all the activities. For USP, meet us at the stairs, and all the rest that stay here just go 2:30. But yes, we can ask one question still.
Okay, no question. So let's thanks the speakers again.